don't see anything yet. Is it?
It's up here. It's on. It's on.
Okay, sorry. Well, I'd like to welcome everybody to this afternoon's session, and this is going to be somewhat different from the regular talks. The goal here is really to have a good discussion about the whole information problem, but perhaps focused from the perspective of islands and fuzzballs and this sort of thing. And so the format is basically, the idea is Juan will speak for about an hour, then Samir will speak for an hour, and then there'll be some back and forth. But in between, I encourage people to jump in if they've got quick questions, and I ask the two speakers to reserve about 10 minutes for questions. And then later on in the evening Paris time, we'll have a panel, and Douglas Stamford will join in and Emma will moderate. But for the moment, Juan is going to kick off, and the subject really is sort of explore the whole sort of set of real estate. My original focus was to try and explore the issue of islands more closely, and in particular try and determine whether islands are a serious new piece of real estate that sort of emerged from the maelstrom, or whether they're just a distracting work of fiction that will ultimately disappear beneath the ocean. One way or the other, I don't expect us to come to consensus. What I really hope for in this discussion is clarity about the issues involved that perhaps lead to a tension or differences between the perspective of islands, the perspective of wormholes and fuzzballs. And without further ado, I'll hand over to Juan for his presentation. So,
okay, yeah, okay, I can see my screen now. Well, thank you for the invitation to give this talk. I'll basically give a review of the ideas that lead to the island formulas. And well, as Nick said, please jump with questions. This talk is similar to other talks I've given. So if you have heard it, you'll find it repetitive, but hopefully we'll all be in the same page, at least in what we are talking about. So I think that the main two papers that led to this picture are these papers of Pennington and Almeri, Engelhardt, Maroff, and Maxfield, who applied the Ruta-Kanagi formula and its extensions in a new and interesting way. And what I'm going to say about here is based on this review that we had. So the outline is first to talk about black hole entropy, and then about the notion of fine-grained gravitational entropy. So we'll see that there are two black hole entropy formulas. And then we'll use these formulas to compute the entropy of radiation coming out of black holes. So we'll apply the formula not to compute the entropy of the black hole, but the entropy of the radiation. And then the final result is that one gets an answer consistent with information conservation as opposed to information loss. And then there will be some interpretation of what this means and so on. So this notion of entropy and the area formula goes back to this very old question of computing the entropy of the universe outside the black hole. And the question was whether it decreases when you throw entropy into a black hole. And Bekenstein famously argued that if you include in the entropy a term which is the area of the horizon, then you could obey the second law of thermodynamics. And this entropy then was further improved to include this entropy outside was the entropy of all, including the entropies of quantum fields, the entropy of the quantum fields outside the horizon. So if you have a Cauchy slice that, well, it also extends inside the horizon, you consider only the portion that is outside the horizon, and you compute the von Neumann or quantum entropy of the fields outside the horizon. And that's what comes out here. So semi-classical means that we are using the semi-classical description, where we have a background and we quantize the fields around that background. And this entropy was shown relatively recently by Aaron Wall to obey the second law of thermodynamics. This is non-trivial because this includes processes such as Hawking radiation and so on, where the area term actually decreases, but the entropy outside increases. Okay, so that's one notion of entropy. And throughout the talk, we'll be thinking about the problem of semi-classical gravity. So we'll think of gravity as an effective field theory. And we'll treat the background geometry as classical, and we'll think about quantum fields propagating on a classical background, including the perturbative gravitons. And the back reaction due to Hawking radiation is treated using the semi-classical equations. This is an approximation that has an effective coupling, which for a, let's say, Schwarzschild black hole is proportional to 1 over the entropy, or 1 over L Planck square over the size square of the black hole. Now, one important point is that things like the energy spacings between different energy eigenstates and so on are very tiny in terms of this coupling constant. They are exponentially small. And so this I take to mean that in order to describe microstates precisely, we might need non-perturbative accuracy. But we'll not be talking about microstates in most of this talk. Now, these results on black hole entropy have inspired very influential hypotheses, and which we like to call it central dogma in the quantum aspects of black holes. And this is the idea that if we have a black hole and we look at it from the outside, it's described as a quantum system with S qubits. So the number of qubits is the area of the horizon. And it evolves according to unitary evolution as seen from the outside. And now here, the word dogma means assumption. So this is certainly an assumption that gravity obeys this property. It's not something that has been derived from gravity. So we cannot start from a gravity theory and derive this property in any case. I mean, more in practice, the black hole is in general in contact with some exterior region. And in order to apply these ideas, we need to imagine having some kind of imaginary cutoff, which separates the sort of outside region very far away from the black hole from the region relatively near the black hole. Exactly what this cutoff is and so on, well, this assumption does not tell us. There are some specific cases like ADS. You could think of this cutoff as being at the boundary of ADS and perhaps then having another theory coupled to ADS representing the region outside the black hole. So that's the best way we know how to define this cutoff in a way that we think it's completely precise. But from the point of this assumption, we don't need to be very precise. We can just think there is some cutoff. And of course, this is we'll have this system with the S degrees of freedom, and it will be coupled to the outside system, which we treat perturbatively. So this is sometimes also said as saying that the black hole is similar to a piece of coal, so some ordinary material that, albeit one that is very strongly interacting for reasons that probably all of you know, dealing with maximal chaos, for example, and quick thermalization. Now, as I mentioned before, it's important to note that this A over 4G qubits, or the exponential number of microstates, are not manifest in the gravity description. Now, sometimes the states in the associated Hilbert space are called black hole microstates. And they are supposed to describe this object as seen from the outside. And this statement is this central dogma is only a statement about the black hole as seen from the outside. There's been no statement made about the inside. Okay. Now there is some evidence for this, which from string theory, that the first evidence was the supersymmetric, the case for supersymmetric black holes in supersymmetric string theories, which can be counted precisely using strings and d-branes. And this reproduced the area formulas, and not only that, but also corrections to the area formula. Now, in some of these computations, the idea is that you start a strong coupling with a black hole picture, and then you dial the value of the coupling. So in these theories, you can have fields whose wave you can imagine changing. And then you go from a strongly coupled picture where you might have a black hole, an extremal black hole, to one where you might have a collection of strings and branes, which are very weakly coupled and which you can count precisely. And so this was the original logic. And the idea was that since these are extremal BPS states, these numbers should not jump. In some cases it jumps, but you can understand the jumps. Yeah. But one question that this has not answered is, can we see the microstates directly at strong coupling using the gravity picture? And I guess part of the progress in Fuzzballs and so on has been in trying to understand that directly at strong coupling and using the gravity picture, direct picture for the microstates at the coupling you are working on. Another evidence is the ADS-CFT, where we think that black holes in ADS can be described by fluids on the boundary. Now, there are also arguments against this picture, and there is the famous Hawking argument. So Hawking's argument involves looking at an evaporating black hole. This is roughly what we expect the Penrose diagram to be for an evaporating black hole. So the central point here is that when we consider the time evolution, we can consider different Cauchy slices at different times, and we find that the process of Hawking radiation can be viewed as a process of pair creation. We create a pair outside and a pair inside, which are entangled. So the total state is pure, so we have unitary evolution that takes us from one Cauchy slice to the next Cauchy slice, etc., up to this, let's say, some Cauchy slices at very late times. And if somehow we imagine that here there is some quick process where we disconnect, so here the black hole is very tiny, and then if we imagine that that evaporates very quickly, and it produces now a flat space full of Hawking radiation, which was emitted during the whole lifetime of this black hole, then this state will be in a mixed state because we don't have access to the interior. So the logic was that the observer who is here in the future has no access to the black hole interior, and therefore can only make observations in this region of the geometry, and his state will be mixed, and the entropy so the state will be mixed, and we went from a pure state to a mixed state. And that's not what we expect if we had this, if we had a piece of code, or that central dogma we talked about was true. That's not what we expected. Now, the skeptic's point of view, or Hawking's point of view, you could say, is can be also described in this way, where you imagine that the process of formation of black hole, the process of black hole formation and evaporation is a process that splits off a little baby universe, or maybe you could call it the teenage universe, because it's a big baby universe. So it contains the whole black hole interior. And we are making observations here on this parent universe. And well, we are not accessing the baby universe, so we have some we have some entropy. So this is not very different from an ordinary process of EPR. When you create an EPR pair, if you look at only one of the members of the pair, you'll see some entropy. Okay, so this can yeah, please go ahead.
When you say that the state is pure, if you include both universes, is that an assumption, an approximation, or
yeah? So in the semi-classical description, right? So here, for example,
so it's an approximation.
Yeah, within this approximation, the state is pure, right? We have no reason for, or at least up to the small corrections that we expect, that, correct the semi-classical approximation. Now, one can quantify this a little more in terms of computing the Hawking curve. So that's the entropy of Hawking radiation computed as a function of time. So first, as we emit the Hawking radiation, this entropy rises monotonically until the black hole evaporates completely. Of course, it's not a straight line, but well, it's some line whose precise shape depends on the details of the black hole. On the other hand, the thermodynamic entropy of the black hole, sort of given by the area of the horizon, will decrease also monotonically as a function of time. And we have a contradiction with this central dogma, not at the very late time, but we have a contradiction at the time where these two entropies are comparable, because here when the entropy of the Hawking radiation starts rising, okay, that's not yet a contradiction, because it could be that this radiation is entangled with these black hole degrees of freedom or black hole microstates. However, at this point, for example, sometime here later, there is more entropy than the number of black hole microstates, or than the number of qubits, and therefore this entropy cannot arise from entangling with a system that has less entropy. So we have a contradiction at this time, which is really far from the time, the last moments of evaporation, which is when we lose control over the semi-classical approximation. So whatever, so if we are, on the other hand, if that central dogma was correct, then as Page observed many years ago, the correct curve should be this curve, this purple curve. That's the maximum entropy that the radiation could have at any time. And so something new should happen at this time, which is a time at which apparently the semi-classical approximation works well. Okay, so yeah.
Let me know if you mind being interrupted. I just had another question about the computation of this green curve.
Yeah.
So what are the assumptions that go into? Because of course I can have to either the black hole or the piece of coal, I can have very small corrections that restore the page curve, right?
Yes.
So in principle, Hawking's calculation is not exact. That can be exponentially.
It's the calculation we get from this semi-classical picture, right? So we take this and if we calculate it using the semi-classical picture, right, we get that answer.
But don't you need to also make some assumption about how the corrections to that semi-classical, because you don't control either perturbative nor non-perturbative corrections to that semi-classical.
You could have non-perturbative corrections to the various matrix elements, and that could lead to, and that would lead to a different curve. And part of the question we are asking is, well, how do you see this? And the issue perhaps is that, okay, there are all these corrections, but if you focus on one observable, such as the entropy, right? This is an order 1 correction, well, or big correction, order 1 over G Newton correction to the entropy, right? That we want to see.
Okay.
So the
Monica,
goal
I think,
here, yeah.
Monica, I was going to say, I think Samir is going to talk about the small corrections theorem. So I think maybe that question is better saved for when Samir gives his presentation. I don't know.
Fine, yeah.
Yeah, here we will focus first on understanding the computation for the entropy. So we want to calculate this entropy. Now, from what this kind of discussion we are having suggests that perhaps we first need to understand the very tiny corrections, and then we will be able to calculate the correct entropy. That certainly was my point of view before these papers were written.
Right. I guess is it correct to say that the green curve in the right hand side is what you'd naively get from this approximate gravity calculation if you assume that the corrections won't conspire to bring the curve down?
Yeah, that's right.
It is a naive assumption, given that you cannot compute them anyway.
Exactly.
Okay,
now, we talked about the central dogma and so on, but in what follows, we will not assume the central dogma. We will, it is somehow assumed in the language we will use, but we will not assume. So we'll do some computations in gravity. And these computations can be viewed as providing further evidence for the central dogma by reproducing this page curve from a gravity computation. So that's what we'll discuss in the next few slides. Now, this computation gives the so-called fine-grained entropy of the black hole. And for that, we need to recall that there are two notions of entropy that we have in this story. One is the so-called fine-grained entropy, sometimes called von Neumann entropy or quantum entropy or entanglement entropy. And this is just if you have a density matrix rho, you calculate rho trace of rho log rho, and that's it. And under unitary evolution, this remains constant. Then we have the notion of coarse grain entropy or thermodynamic entropy. And you could say this arises from some sloppiness. So we don't measure all the observables, we measure only a subset of the observables. And it has some definition I will not enter into the details of. But in this entropy can obey the second law. So it can increase under unitary evolution. Even for an isolated system, it could increase because of the growing complexity of the state that prevents us from measuring certain observables. Now, so it's okay for the coarse grain entropy to rise, but it's not okay for the fine grain entropy to rise, right? So if we had this page curve, so we look at the entropy of the Hawking radiation and we are computing the coarse grain entropy, it is fine that it rises and so on. It maybe arose because we did some approximation. But so the entropy that should obey the page curve is the fine grain entropy. And one might think that the gravity only allows us to compute the coarse grain entropy. But the recent news is that we can actually compute the fine grain entropy. And for this, it's crucial to account the interior geometry. And so we'll discuss now the computation of the entropies of the black hole as seen from the outside. So first we'll concentrate on the entropy of the black hole. And the horizon area computes the thermodynamic entropy. And well, the main reason is that it obeys the second law. And how can we compute then the fine grain entropy? Now, so the computation of fine grain entropy goes back to ideas of Ryun Takayanagi that were sort of expanded by various people. And this led to the proposal by Engelhardt and Wall of a formula of this form, where you compute this generalized entropy expression, where you compute the area of a surface and the entropy of the quantum fields outside the surface. So you choose some surface, which could be the black hole horizon, but it could also be some point in the interior or maybe even in the exterior. And you compute the entropy of the quantum fields on this slice. You add the area, and then you extremize with respect to the position of this point. So you start moving this point, and you find an extremum where if you move it up and down or left and right, this entropy doesn't change. Now, it might happen that there are more than one such extremum. And if there is more than one, then you choose the minimum, the one that has the minimum value of this quantity. And the surface that extremizes are sometimes called quantum extremal surfaces. I mean, it's really a classical surface, but it minimizes this quantity. And the minimum of all of them is sometimes called the minimal quantum extremal surface. Now, it's crucial that we are allowed to take the surface to the inside, and so the final answer will depend on the geometry of the interior. So here, yeah.
Sorry. I have a question about how you actually define the basically the surface whose entropy. So the original Wall-Engelhardt proposal was for a surface that was anchored on the boundary. So I also had a dual, but also it was clear because I was fixing the endpoints of the bulk surface and then minimizing this quantity. In your case, it seems that you're choosing some surface that lies entirely in the bulk, roughly the intersection of your green and
If you want a completely let me just interrupt you for a second. So if you want a completely well-defined setup, then you can take this line to be an ADS boundary.
But then I'm not computing the entropy in flat space or in some sort of quasi.
Yeah, you could think of this as being ADS coupled to some flat space.
So I think that setup, indeed. Yeah,
that setup is good. Now, I think for the purposes of what I'm talking about here, we could think of this as a surface that has a fixed area. So you take a cutoff where this surface has a fixed area, okay, and it's somewhat far from the black hole. And so there will be, when you compute these entropies, there will be an area divergence here, but this area will always be constant in the whole discussion. But you can continue to apply these formulas.
You mean, is this some, because I would have thought that maybe I can define things by like relative to some boundary that I may have, or maybe even with some interval on scribe class or something like that. So why is this?
Yeah, you could, yeah. So for something that is a bit better defined in flat space, and some authors have discussed that, they define some intervals here at infinity. I chosen not to do that because, well, this putting a cutoff somewhere, it's a little more intuitive of separating the black hole degrees of freedom from the rest. And for the purposes of these entropy computations that we're doing, we can do this and we get the right answer. If we want some more detailed observables and do computations with non-perturbative accuracy and so on, then we might need to do, we might need to take this surface to infinity.
Yeah, maybe I can, yeah.
Can I ask, what is the regime of validity of this formula? Why can I use it?
Well, the idea is that this formula should be applicable whenever, roughly speaking, whenever the semi-classical description is correct.
But if you start, in a sense, following time and going, in a sense, closer to the singularity, at some point, it's not going to be applicable.
Well, I mean, I'm imagining this surface here on the boundary. This cutoff surface is always away, I mean, far from singularities and has fixed area. So you can apply it at any time for this cutoff surface, and we'll discuss various times in what follows. This point here tends not to get close to the singularity. I mean, we move this point, right? And this point in most examples is not close to singularity. And but yeah, maybe there is some interesting set. I mean, in fact, it would be interesting to find a setup where it gets closer and closer to singularity.
And is there a definition that does not rely on semi-classical approximation?
Well, the first approximation, no, but people have discussed in the context of quantum error correction and so on some analogous definitions where there is a piece that can be viewed as an area piece and a piece that can be viewed as the semi-classical entropy. But yeah, for the purposes of this talk, this is a formula that applies whenever we have a semi-classical gravity description. You can view it as a different version of the Bekenstein-Hawking formula. So Bekenstein-Hawking formula computes the coarse-grained entropy. This formula computes the fine-grained entropy, but both of the formulas arise when we have a good semi-classical description. There are some subtleties with this formula when there are two extremal surfaces with comparable entropy, and these subtleties were discussed by Akers and Pennington. But I think these are some special cases. So for first approximation, we should just.
And also the second piece, the semi-classical, is it clear that applies even to perturbative gravitons?
Yeah, this. I think it probably applies. You can define some boundary conditions so that the computation appears to be well defined. We set some boundary conditions in a paper we wrote with Jeffers and company. But no, as far as I know, no one computed it explicitly for some case. Well, maybe for JT gravity was computed, but you could say in that case you don't have gravitons. Yeah. But for most, so I think it's probably well defined for gravitons also. And any subtleties with gravitons have to do with what happens very near the surface. And as we will see later, all the interesting aspects of this formula come from the properties of entanglement far away from the surface. And those for gravitons or not gravitons would be essentially the same. So we, at least I don't expect that there would be difficulty with the gravitons.
And once you have dynamical gravity, you also have Gauss's law, and then defining if defining the entropy, separating, intervals, it becomes ill-defined.
Yeah. So I mean, here you should, you would have to think that you first take a background space-time, and then you perturbatively quantize all the fields, including gravity. And yeah, as you say, there are some issues with choosing gauge and appropriate boundary conditions for the graviton. I think we chose some boundary conditions that work, but no, the explicit computation was actually not done. So I cannot honestly tell you that there is no problem.
Yeah, thanks.
Sorry, just a small question. I want to make sure that I didn't misunderstood. So this cutoff surface area that you have shown in this Peros diagram is the same that you mentioned also when you introduced the central dogma?
Yes, it's the same, yeah.
But you just said to Monica that basically this surface is the area is constant, but it should decrease during the evaporation, right? That's the whole point for the paradox.
Well, it's in principle you can choose whatever you want, but I think for the purpose of this discussion, it's a little conceptually more clear to choose this surface to have a constant area. I mean, you can imagine you pick a surface, your cutoff is you pick it at some instant of time, and then you propagate it to the future, right? And you just choose to have constant area. That I think this is conceptually more clear, because then the divergence that comes from the entropy of quantum fields will just be constant in time.
I see. Now it's very difficult for me to think about this just for instance, let's take a 4-dimensional Schwarzschild black hole.
Yeah.
And I mean, how to really precisely define this?
Well, just pick some surface of constant area outside the black hole. So you might need to, so pick a surface of a Schwarzschild black hole at constant r, and that will have constant area in Schwarzschild coordinates.
But then if you say that, and then you would say that basically the entropy of this black hole system would be just the area of this surface?
No. The entropy will have a piece that will be the area of this surface. That we are not really
the number of degrees of freedom, I mean, yeah.
But the interesting piece will come from the area of this surface and the entropy of the quantum fields in this region.
Maybe we should let Juan move on, and then pick up the questions at the end.
Okay, so here is the first interesting calculation. So we suppose a star collapses into a black hole, right? Then from the point of view of Hawking and Bekenstein, there is a non-zero entropy, right? That forms, so because the horizon forms, and then we'll have a growing entropy. But from the point of view of this fine-grained entropy, there is a zero entropy, because you can take the surface and look at the surface with zero area at the center of the star, and you find that the entropy on this surface is equal to the entropy of the original star, and we get what we expected for the fine-grained entropy. So I believe this is an important example where you see the difference between fine-grained entropy and coarse-grained entropy, and you also see that the interior matters. So to compute the fine-grained entropy, what you have in the interior really does matter. In particular, it matters that you have this star. So if you think that the black hole will form into a bunch of fuzzballs or whatever at this time, then you cannot easily compute the fine-grained entropy. But with this space-time picture and following these rules, you can actually compute the fine-grained entropy, and you get the expected answer. And I should emphasize that the formula for fine-grained entropy was invented for other purposes. It was not fine-tuned or invented to describe this. So it was later understood that you could use it to describe this property. Now, at late times, we have a problem, because if we're at very late times and we want to compute the entropy on this slice, so again, this is still an extremal surface where this area is zero. And here we have all the partners of Hawking radiation that, let's say, have left the system, and they contribute to the entropy, and they contribute a large amount to the entropy, and they contribute an amount which is bigger than the area of the black hole at this time, if we are late enough times. So there we seem to have a problem. And the solution to this problem was given in these two important papers. And the main realization was that there was a second quantum extremal surface that lies close to the horizon, that so that the entropy that you capture is basically, you don't capture much of the entropy of the Hawking modes, and you get an answer which is essentially close to the area of the horizon at late times. Now, in detail, it's maybe somewhat difficult to find exactly it's hard to find in practice this surface, but there is a general argument that there should be one. I was given in this recent paper by looking at whether the entropy decreases or increases as you move the surface in one direction or the other. So now we have two quantum extremal surfaces. So we have the one that goes all the way to the center and whose entropy increases monotonically up to the evaporation time. And then we have this other one whose entropy is actually decreasing because the entropy is almost equal to the area of the horizon. And so it's going down, and we're supposed to choose the minimum of the two. So for some times we choose this one that goes all the way to the center, whose entropy is increasing. And then at the page time, we choose the other one, which has lower entropy. And by the combination of the two, we get that the entropy of the black hole sort of rises and goes down as expected from this central hypothesis. Now, in these computations, we computed the page curve. So we reproduce something that looks like the page curve, but for the black hole. And we really wanted the page curve for the radiation. Now, radiation lives in a region where quantum gravity effects would be very small. It could have left the ADS space. It could be collected in a quantum computer. And we might think it's straightforward to compute the entropy of that radiation, just you use the semi-classical expression. But because we obtained the state using gravity, the idea is that we should continue to apply the gravitational fine-grained entropy formula. So the fact that we obtained the state using gravity enables us, or entitles us, or maybe you could say obliges us to use the to again use the fine-grained entropy formula. And this formula, in principle, we should allow. So in the previous discussion, we always had connected regions that were appearing, but there is no reason why the regions should be connected. And so we could have a disconnected region, sometimes called island, in the black hole interior that appears when we are computing the entropy in the outside. So here we are computing the entropy of the radiation outside the black hole. And this entropy will be large at late times due to, if you compute it only here, it's the entropy is large due to the Hawking radiation. But if you include a region also, if you also include the black hole interior, you can decrease the entropy because you get the pure state for the Hawking modes and the partners, and you pay some price, which is the area of the surface. But depending at what time you do the calculation, in particular if you do it at late times, then this might be more convenient.
Sorry, one quick technical question. You're actually using a model in which you actually have this Penrose diagram for the computation, or you use ADS glued to flat space?
No, you could use ADS with flat space if you have to. You could do it in this case also. I mean.
But has it been done, or?
Well, I mean, not very explicitly, but you would get this answer I'm telling you about. You would need to use you wouldn't do it explicitly, you just use the results of this paper that ensure that there will be a quantum extremal surface near the horizon.
Sorry, can I ask a question?
Yes.
Sorry, okay, so here, if you are purifying the state of the outside radiation by including this island inside, well, this is good, but I mean, after the full evaporation, you are still left with the outside the radiation in a mixed state, but there's no black hole anymore, so there's no island anymore to purify your radiation state.
Yeah. So well, I agree with everything you said. Sorry to interrupt you. I agree with everything you said, except the fact that there is no island. There continues to be an island, and I will have a picture about that in just a second.
Okay, thank you.
Okay, yeah. So
can I ask also a question here?
Yeah.
So suppose I'm an observer at Sky Plus,
Yeah.
where gravitational field is very weak and some
Yeah.
radiation is coming in.
Yeah. Yeah.
How would I tell that just using the usual quantum field formula, quantum field theory formula on radiation, that formula is not correct?
Yeah. So you would tell by asking, where did I get this state from? So if you got the state by doing, if you got the state by using the gravitational evolution, then you should use this formula.
But suppose I'm just observing. I don't know what happened in the past. I'm just seeing some photons coming.
Yeah. So if you're an observer and you are really good observer that can measure everything, then the answer you will get is supposed to be the same as the answer you get using this formula. But if you're a calculator, right? So if you are calculating what such an observer would see, and you calculate using just the semi-classical space-time, and you only look at the radiation at null infinity, then you would get the wrong answer. That's what Hawking did, and the idea is that you get an answer which is approximate, and you made a mistake because of not including non-perturbative corrections. So the miracle of this formula is the following. Maybe I should emphasize it, and this has to do with with your question. The miracle of this formula is that the left-hand side gives us the entropy of the exact radiation state. So the exact radiation state is not something we can easily compute using this semi-classical description. We don't know really how to compute it using the semi-classical gravity description. But this formula promises that if you manage to do that exact computation, then the entropy is approximately given by this quantity. Okay, so this quantity plus higher order Newton corrections. So if
I'm a substatic observer, then I really need to know what happened kind of deep in the interior of the space-time to be able to reliably do the computation.
Yeah, if you are doing the computation, then you need to know about the interior. If you are someone who measures, you don't care. You just measure, and you are supposed to. If you do exact measurements, you're supposed to get this answer. So this formula gives us a method for computing some property of a state that we cannot calculate. So the state itself we cannot calculate, but we can calculate its entropy. That's the promise of this formula.
But one, sorry, John, maybe I'm sharpening Costas' question. Are you postulating there are two different kinds of photons in infinity, those which come from burning coal and those that come from evaporating black holes, and their difference is somehow the photons that came from a black hole have some entanglement with an island deep in the interior? Because if I follow Costas' viewpoint, I'm in infinity. I just see photons, and they're photons.
Yeah, there are photons. Yeah, so if you're an observer at infinity, you see photons, and if you measure well enough, you'll see that they're in a pure state. That's the idea. This is what we think it's true. All we can, but that doesn't follow from what I'm talking about. So what? So we are doing a gravity computation that gives us some entropy, which we think is the approximate entropy of the exact state. That's all that is done.
But I would have thought, if I'm again an observer in a place that doesn't have very weak gravity, that I'm able to compute reliably.
The observer. We should distinguish the observer that measures and so on, the experimentalist, let's say, and the theorist. The theorist does the calculation.
Let's be a theorist. So let's be a
So if you're a theorist, then if you just you could give some approximate answer, which will have large entropy, and that should be viewed as the coarse-grained entropy of the state. But you could do better. So as a theorist, you could do better, and you would do better by including the island. So by knowing how you prepare the state and including the black hole interior.
But if I am in the Sky Plus, I wouldn't know whether there was a black hole or that's in a sense outside.
Well, but if you are a theorist, you know how you prepare the state, and if you prepare the state using this process, then you need to use this formula. I mean, if you're sort of theory,
So
good practice theory would I ask you to use this formula. And
but are you saying that there's a very small entanglement in the photons at infinity that if you measure to arbitrary accuracy you would see that? Then surely that would be
yes,
covered
that's
by...
the idea. That's the idea. That's
So-
but that's
so-
a hypothesis. It's not something that's yeah. So all that
isn't that kind of ruled out by the small corrections theorem? But okay, we'll have with that with Samir later.
Well, we discussed the small correction theorem and how I think the small correction theorem. Well, maybe I'm not sure whether to jump directly to that or. Well, let me go in order and.
Yes, go ahead, please.
So can I ask a question still here?
Yeah.
Okay.
So
look, go ahead. I can extend the time a bit, but go ahead.
yeah, so I just wanted to ask, so to apply this formula, it seems like you need to know the state of the quantum fields on Sigma Island.
Yes.
Which an external observer can't see. So
yes.
There's an assumption, there's a hidden assumption here that you're constructing the state of the quantum fields on Sigma Island by assuming that the Hawking process is taking place
yes.
at the horizon.
Yes,
okay.
yes. You got this state from some particular history, and you need to use all the information that this space-time diagram is giving you, and the formula tells you how, using this information, you can calculate an expression for the entropy of the exact state.
Okay, so the state on Sigma Island, you have to know the entire history of the black hole up until the time of the Cauchy slice, and you have to assume that the Hawking process is going on at the horizon.
Yes.
Okay, thank you.
Yes, I mean I mean, in principle, you would need just these. Well. Okay. So the. Okay, let me skip this. So now you can make a complaint about this. You could say, well, this is just an accounting trick. I mean, you could say, well, the skeptic would say, well, I always said that if you include both the baby universe and the black hole exterior, you would get the pure state. But the whole point is that you don't have access to the black hole interior. Now we should view this more, instead of a trick, as a little bit of an oracle. I mean, this part of the point here is that this formula is not just made up, but it can be derived from the gravitational path integral. And I'll just review in just a moment that it can be derived. And it's in a sense an oracle because it gives us the fine-grained entropy of the true state, but only using the semi-classical state. It's kind of a little miracle that by using purely the semi-classical state is giving us the entropy of the exact state. Now, I probably be quick about the derivation of the RT formula. It's basically the same as the computation of the Gibbons-Hawking entropy. So it has the same sort of advantages and disadvantages. And given that amount of time, I'll just skip over these transparencies. Okay.
Juan, since you're skipping, can I just ask some things?
Yes.
Maybe you can,
yes.
This was Euclidean, but your formulas were Lorentzian. Can you comment on this?
Yes. So yeah, these pictures are Euclidean, but the idea is that even if you had a Lorentzian setup, you could derive a similar formula by thinking about evolution backwards and forwards in time, so through Keldysh-like contours. And so you would have, for example, here you have 3 copies of the density matrix, and you would have to put these Keldysh contours going back and forth. And there would be in the end some partially Lorentzian, partially Euclidean solution that computes that entropy. And there have been some recent papers, so Marolf, Rangamani, and others and collaborators who have analyzed in more detail this problem of finding the Lorentzian, the proper Lorentzian picture. Now, in some situations, you can say, well, I computed in Euclidean space and do some analytic continuations, but I think the logic of these formulas also extends to the Lorentzian.
Maybe I can ask. So this here you're using the replica trick. I mean, but that's a computational trick. So if this formula is a true formula, one should be able to derive it in a way that doesn't use that trick. Is there any way to see the same formula without using the replica trick?
I don't know. I don't know how to get it without the replica trick. But yeah, I agree with you that maybe there is some other way to get it. So, so the replica trick has the advantage that it connects it more directly to Gibbons-Hawking, and I mean it's essentially the same as. So the difference between Gibbons-Hawking and this is that in Gibbons-Hawking you have a U1 symmetry on this circle, and here you don't. That's the only difference. And I guess one point I wanted to emphasize is that as in the Gibbons-Hawking derivation of the entropy, you are not summing over microstates. So you get the final answer, but you don't see what the individual states are. So that's this formula has the same, if you wish, advantages and disadvantages as the Gibbons-Hawking formula.
Yeah.
So far we've talked only about entropy, but what is this saying about the interior? And this has to do with, again, going back to that central dogma of whether those degrees of freedom that appear there that describe the black hole from the outside also describe a portion of the interior or not. And that's the question, is whether those degrees of freedom describe all the interior or what part of the interior. And the answer is that they describe a portion of the interior, and the particular portion is called the entanglement wedge. So let me just remind you what the entanglement wedge is. So when we computed the entanglement entropy, the fine-grained entropy, we had some region, and if you look at all the points in the space-time that can be determined from initial data on that region, that's the entanglement wedge. So let me give some examples. So for example, for a black hole at early times where we had a slice that went from here to the center, so this whole little wedge is the entanglement wedge of the black hole. So the idea is that anything that is going on here, we could recover from the so-called black hole degrees of freedom, or from doing measurements here outside in this region. And similarly, if we have the radiation outside, then this would be the entanglement wedge of the radiation. Now, when we have the island, then the black hole degrees of freedom, or these degrees of freedom of the central dogma, do not allow you to describe everything in the interior, only a region that goes up to slightly behind the horizon. So a small region here in green, and then this island region, which could be, in principle, determined by doing complex measurements here on the radiation. So the idea is that anything that goes on in the island region could be obtained by doing arbitrarily, very complex operations on the radiation. This is a hypothesis, and you can sort of argue that this hypothesis is true by thinking about wormholes and thinking about some sort of replica trick-like computations for computing certain observables. And I was asked the question of what happens after the black hole evaporates completely. So in that case, if you look at the region inside the surface, you have flat space, and this is the entanglement wedge. And then you have radiation here outside. The black hole has evaporated completely, but we should still have an island, which in this case now covers the whole black hole interior. So that's the picture for late times.
Can you say some more about this? Because what black hole interior if the black hole has fully evaporated?
Well, this region of space-time continues to, I mean, it exists in some place, right? And the idea is that if you have some qubit, some probe qubit here, the state of this probe qubit in this region can be determined from doing a measurement here on the radiation. I mean, this this region of the space-time is sort of yeah, it's some other. This is like the baby universe we were talking about. So this region behaves a bit like this baby universe, and the idea is that this whole baby universe is described by the radiation. That's the hypothesis.
So what's the difference between this and those remnant theories? It's just you have some black hole
the point
left
is that So the point is that in the remnant theory, you here you don't have flat space. You have some object at late times. Here you have flat space, and there is this other region existing somewhere else in superspace, and it's the quantum information here is can be recovered from operations on the radiation.
I think I'd like to ask everybody to hold their questions to the end, because Juan's got another 5-10 minutes, and I'd like him to finish his story, and then by all means we'll move on. But let's let Juan finish out.
Yeah. So the idea. So here, something crucial here is that part of the interior is really described by the radiation, and this is an important point. So the idea is that by performing a complicated operation of the radiation, we can extract the information from the interior. And how exactly this happens? Well, maybe we can create a wormhole connection to the interior and get it from there, or maybe using the bulk modular Hamiltonian. But in general, it's difficult to get this information through unitary operations. Now, I was asked a question about the AMPS paradox, or the Mathur's small correction theorem. And I think this type of paradoxes involve involve the central dogma that we talked about, plus one further implicit hypothesis. And that is that the interior operators, so the ones that act on the interior Hilbert space of the black hole, act on the same Hilbert space that appears in the central dogma. So the same Hilbert space of that are describing the black hole as seen from the outside. But with these ideas, we think that this is not correct. So that's somehow the way out. So to be a little more explicit, so in, for example, AMPS and also in Mathur's small correction theorem, there are these two modes that are entangled. So the Hawking radiation mode and its partner. And when we're talking about late times, so this will exist here within the black hole Hilbert space. But this one here is supposed to be part of the radiation Hilbert space, okay? And so in that way, you avoid the problem. Now, it's important in this discussion not to confuse the following two things. So one is the degrees of freedom that appear when we want to describe the black hole as seen from the outside. So the so-called black hole microstates, okay? So that's some Hilbert space and so on. And another thing which is different is the quantum degrees of freedom in the space-time geometry that are in what's sometimes called the interior of a black hole, okay? So the idea is that, unfortunately, you could also say, okay, this belongs to the black hole, but these are two different notions. So there is the notion of the degrees of freedom describing the black hole from the outside, and then there is the notion of, well, some quantum fields that live in this space-time geometry. And what we are doing here is we are kind of dividing the space-time geometry and assigning a portion of the space-time geometry to the radiation and another portion to these black hole microstates. So I think that, yeah. I skipped this comment. Maybe I'll skip this question. Now, often in this discussion, this discussion we were having about the black hole interior is intimately connected to the discussion of the bags of gold. So these are space-times where you have, let's say, some exterior, then we maybe have some horizon, and you have a very big universe inside with lots of entropy, an entropy which is bigger than the area of the horizon. And these space-times were viewed as problems for black hole entropy. There are definitely problems for thinking that the black hole entropy describes everything. I mean, that the area of the horizon describes the entropy of everything that is inside. And the resolution to this is that the exterior degrees of freedom, or the microstates, describe only up to the extremal surface here. And then the rest somehow belongs to someone else. And so this, I was saying, is intimately connected because if you look at the slice at the late times, this slice has a geometry which contains a small neck. And then here it can contain a large amount of entropy due to the partners of Hawking radiation. So the pattern of entropy and geometry is similar to the bag of gold. Let me make a comment. So sometimes we think of, people say that gravity is like thermodynamics. And this is fine if we think about the semi-classical description of physics outside the horizon. And it's definitely what we expect from thermodynamics, hydrodynamics, and so on. However, once we include the black hole interior, we are keeping more information. And we really can compute, for example, the fine-grained entropy and so on. So it's the full space-time, including the interior, is more than hydrodynamics. Okay. And for example, for some black hole microstates, such as the ones produced by collapse, it's important to keep the interior to get the right fine-grained entropy. So some in conclusions, we reviewed the gravitational fine-grained entropy formula, and we applied it to the computation of Hawking radiation and obtained results consistent with unitarity. And this formula suggests that the interior is part of the radiation, not part of the black hole degrees of freedom. What was Hawking's mistake was not to use the fine-grained entropy formula. He just used the coarse-grained entropy formula. One point is that you only need to use gravity as an effective field theory to apply these formulas. Now, is the information puzzle solved? Now, one aspect of the information puzzle, which is to compute the entropy, I would say it is solved in the sense that, well, you get the answer for the entropy. But there is another aspect, which is that you want to understand what the state is, so what state comes out of the black hole, and that, I would say, has not been solved. So these replica wormholes and so on, they are useful for computing the entropy, but they don't tell us what the actual answer is. I would say that these formulas are completely analogous to the black hole entropy formula. It is some accounting oracle that tells us what the entropy is, but it doesn't tell us about the microstates. And okay, that's the end. I had here. Well, yeah, maybe I just end here.
It's good. You're going to get another 15 minutes in due course, Juan, so that'll be great. So here's the plan. I want to spend 5 minutes just fielding quick questions. The whole rest of the day is given over to discussion. So if there are burning questions, let's spend 5 minutes, and then we'll start Samir at 16:10. So Francesco has his hand up, so go ahead.
Yes, thank you. Yeah, I have many questions, but given that you said just 5 minutes, I will
pick the best one.
Just the one that I think is very fast. So in the central dogma, what is the area that you were talking about? Because
the area of the horizon.
The area, but then you were describing an area that was constant. I was a bit confused about it.
Okay, maybe I should. Yeah, I was. Yeah, that area that would be constant would be the UV dimension of that Hilbert space. But the area of the horizon is the dimension of the states that are excited and are relevant for the dynamics. So in the case of, for example, ADS, that area that was keeping constant would be infinite. That would be the whole set of UV degrees of freedom. But the area of the horizon would be the effective dimension of the Hilbert space that is excited by the black hole, or where the black hole lives.
Okay.
One. Yeah.
And I will ask the other questions later then.
Yeah.
Thanks. Andrea, you are next.
Yeah, so before you said that in order to know about the existence of the islands and in order to compute the entropy in this way, you need to know about the entire history of the black hole up to the point where you do the computation. So does that mean also about the star that then collapsed into a black hole when there was no issue about horizons and?
Well, yeah. So to be a little more precise, what you need to do, what you need is if you're at some point on the boundary, you need to consider the full collection of Cauchy slices that end at that point on the boundary. So so that whole wedge, sometimes called the Wheeler-DeWitt patch. But so that whole region is necessary. You need to know about the spacetime there because the minimization process allows you to move the area within this region. You're instructed to find within this region the extremum. And so you need to know that the spacetime within that region.
So can I then interpret the island as the purifying system? So before you had all the information about the state, then you have the black hole and you do Hawking evaporation and you do some coarse graining, or you trace something out and you want to sort of recover the information that you had in the history of the black hole, which was a pure state where you in principle knew all about the state. So is it fair to say that this is a geometric incarnation of the purifying system that comes from your previous knowledge of the state before black hole evaporation happened?
Well, I don't want to use the word purifying system. So in the semi-classical description, it is the purifying system. But I think in the exact description, the state is already pure. And
yes, but then you have Hawking evaporation and you just collect those quanta. And so the island is what purifies it after the whole black hole evaporated.
Yes. In the semi-classical description, in the space-time description, the island is what purifies the Hawking radiation. But the idea is that in the exact description, the island is somehow contained within the exact radiation state and is part of that pure state.
I think we should move on. There'll be plenty of time to ask questions during the panel, but there's a couple more questions we fit. Monica, I think, was next, so go ahead.
Yeah, so I'm still a bit confused about your choice of surface where to measure this. So suppose that you told me at some point that I could just think of it as some boundary, like the ADS or some flat state boundary. Should I expect to have, since I'm computing a fine-grained entropy, shouldn't I expect this entropy to be zero or constant at all times, since I have information about the entire spacetime due to holography?
Yeah, so if you want to put this boundary at the ADS boundary, then to have the story that I was discussing, you should also couple the ADS to some external system where the Hawking radiation would move to that external system.
But that's a very different setup from what you discussed, right? Because you're collecting, you're putting your collecting guy outside of the gravitational region, and I'm perfectly fine with that.
Yeah. So you could think that I mean that imaginary surface separates the region which we are going to in which we are going to do the computation from a region where we think gravity effects are negligible.
Yeah, but your formula has a 1/G Newton in it, right?
Yeah.
So I would think it's problematic to take G Newton to 0.
Well, if you don't, okay, fine. So if you don't like this, so just put this boundary at the boundary of ADS. So that.
But then it's constant, right?
What?
But then there's no page curve, right? Because
Well, you put the boundary, you put this at the ADS boundary, but you also couple. Sorry, I misspoke.
Right. Okay. Good.
You also couple ADS to some flat space field theory with no gravity, and the Hawking radiation then moves. So the black hole evaporates into this flat space region, and yeah. And
I see. And
you can have another go later, Monica. I want to get one more question in. I've got to Lakshmi. I think you were next if you want to get a quick one in, and then we'll go over to Samir.
So you also mentioned that there is the second quantum extremal surface that when we were discussing this fine-grained gravitational entropy formula, right?
Yeah.
So has that been like put in by hand, or is it so just because we need to get a finite entropy?
No. Well, the existence of these surfaces is a property of the space-time, and in these two papers that I highlighted, they just derived they calculated where the surface is in some specific theories. So the Pennington paper had a more general discussion, but not a very precise calculation of the entanglement entropy of the quantum fields. And the other paper had a very specific toy model and a very clear, explicit computation of the field theory part.
Okay.
Okay, at that point, I think I'd like to save the questions for later. I'd like to hand over to Samir. So Samir, can you connect to your laptop? And let's thank Juan very much. That was a great presentation. So thank you, Juan. And please, Samir, connect your laptop.
So should I try to do screen?
Yes, go ahead. So over to you, Samir. Thank you for presenting.
Okay, so can you see the screen and also the cursor on it?
Yep.
Okay, great. Okay, thanks very much for the invitation to talk here. I just want to compare what I understand about black holes from the fuzzball perspective and what I have been trying to understand from all the different papers on what I'll roughly call the wormhole paradigm. So let's see if I can advance slides. Okay, here's my outline. I'll first just give a summary of the black hole information paradox, which one actually already did very well. Then I'll be very brief to summarize what the fuzzball paradigm is, because in this audience, most people know that better than me. Then I'll spend some time on the small corrections theorem, because this is what concretizes for me what kind of non-locality one must have in a theory if somebody says fuzzballs is not the correct paradigm. So for me, the whole story is either you have fuzzballs or there will be some kind of non-locality. And I've been trying to understand the non-localities that come in the wormhole paradigm. So then I'll talk about some difficulties I have had with the arguments I have been reading about in the wormhole paradigm. And in the end, I'll end with a philosophical question that perhaps this difference of opinion that we are having between the fuzzball paradigm and these more non-local wormhole paradigms really goes back to what lesson we should draw from the success of ADS CFT duality. And I will then try to say what my view is on where the conflict is coming from. Okay, so let me start with the black hole information paradox. And you just take a star in some pure state psi I, psi initial, and it undergoes gravitational collapse, this classical, semi-classical picture, all the mass goes to singularity, you're left with a vacuum region here, and you can write the metric in these kinds of coordinates. And the important thing to extract from this is that for the region outside the horizon r greater than 2m, if you want to make a complete Cauchy slice, the space-like slices would be like t equal to constant, while inside r equals to m, because space and time have interchanged roles, the space-like slices are more like r equal to constant. And this is what causes the entire root of the problem. Here I have drawn the black hole in Eddington-Finkelstein coordinates. So you can think of this u as some kind of time, and the radial coordinate r is in the horizontal direction. Here is the r equals 0, here is r equals 2m, and you're going to r equals infinity on the right. So the space-like slices look like this. They are t equal to constant outside the hole, and then inside they are r equal to constant, and you can join them smoothly like this. And so what you learn from this is a couple of things which are both crucial for the information paradox. Firstly, there's an infinite amount of space inside the black hole because r equal to constant is infinitely big, and that's where the puzzle will come from, because that's where we can store an infinite amount of data. And then on the other hand, we also see that these slices are not all isomorphic, as you cannot actually slice the entire geometry. The slices which have the same geometry as the earlier slices, and in that situation, you're going to get this kind of stretching of slices. And whenever the slices are not all isomorphic, typically you will get particle production. And so you get these entangled pairs being produced around the horizon. I've just called the members of the entangled pair as B1 and C1, and then on a later time slice, B1 moves to the right, C1 falls inside, and you get a new pair B2, C2. And when B1 and C1 are entangled, you can take it as a toy model. You can write the entanglement as 0, 0 plus 1, 1. And so when you have one pair, the entanglement of the outside with the inside is log 2. In Hawking's leading order calculation, I just wrote leading order over here. When you have two pairs, it becomes 2 log 2 and so on. So the entanglement is monotonically growing. So if you just plot this graph, so-called page curve, the entanglement monotonically grows with the number of emission steps. Well, for a normal body, of course, you think it should come down after some time. So then, because if you have this kind of a situation, once you get near the end point of evaporation, you definitely have a problem, because if the black hole evaporates away completely, then you're left with these quanta which are entangled, but there's nothing they're entangled with. So that's a loss of unitarity. There's no quantum mechanics for that situation. And then if you leave it as a tiny remnant, then you have the entanglement with that remnant to be this large number, n log 2. And then you could ask, how can a small remnant hold such a large number of states? Now, of course, if you agree that there can be baby universes or remnants, then you can say, okay, that is my answer. And perhaps that's what Juan was saying towards the end of his talk, that maybe you can be happy with a scenario where you have baby universes, but then that would be a very sharp distinction between what you see there and what you see with fuzzballs, because the fuzzball just will look like a piece of coal and everything will just come out. So it will be good to pinpoint that later during the discussion session. Anyway, it will also be important to see some alternate versions of the information paradox. One way that people look at it is that you keep letting the black hole evaporate and therefore creating these entangled pairs. That's the radiated guy, that's the infalling partner and so on. But you also keep feeding in positive energy quanta from outside at the same rate at which the black hole is evaporating. So you maintain the black hole at the mass, which is around m, but then the amount of entanglement you can generate between the outer and the inside can be arbitrarily big. So the entanglement entropy S end can be much more than S Bekenstein. And then if somebody wanted to say the black hole has only S Bekenstein number of states, then obviously you can't entangle by more than that. Again, if you have remnants or baby universes, this is not necessarily a contradiction. But if the black hole were to behave like a piece of coal, then this is another version of the puzzle. This conflicts with that. Or you could even forget about the whole radiation thing and just look at the bags of gold puzzle, as it is called. Just because you have this infinitely long slice, you can put all these quanta on it, let's say alternatively with positive and negative energy, and then total mass remains at m. But because you can put an arbitrary number of these quanta, the amount of entropy you can store on it, and therefore the amount by which you can entangle this with the outside, if you want, is unbounded. So it again can be made much more than S Bekenstein. And then it's not so easy to say, okay, I'll have some theory where I postulate that for some reason which I don't know, you can't make very long slices. Now in the classical geometry, you can make it infinitely long. But suppose somebody comes and says, there is some reason which I'm not really giving you, but my postulate is I can't make a very long slice, and therefore I don't have a problem. There's something here to be careful about. It's not that simple, because if you look at the geometry of this slice, it's actually the forward time directions here in this green arrow. It's just like a cosmology, it's a homogeneous but not isotropic cosmology, which is going towards a big crunch. This is the big crunch. So here I've drawn it down here. I mean, normally you can draw a space-like slice horizontal. It's heading towards the big crunch. And if you say that you can't actually have an arbitrary long slice, then you have to go and worry about how our own universe, which looks like a flat cosmology, why do we allow it to be infinitely big the way we think about it? You can time reverse the Big Bang to the big crunch, and then you have to compare these things with what you're seeing in cosmology. So any new postulates you make for the black hole, you have to go and compare them with what you also need to then make for cosmology. So if you want to resolve the bags of gold problem, you don't have to worry about the fact that sitting inside asymptotically flat space. It's not just so easy to say that you can make the slice not infinite. Anyway, these are just different versions of the black hole puzzle, and they all really come from the fact there's so much space here, and you can have both positive and negative energy quanta, so you can entangle with it by an arbitrary large amount. And so what are you going to do about it? Okay, so here's the fuzzball paradigm, a very brief summary of it, and lots of people have worked on it, done much more about it in recent years than I can even follow. But here I'll give you a very brief summary of what it is and then just move on from there. So all we find is that in string theory, when you try to make a bound state of branes, at weak coupling, you might have thought any bound state would have size like Planck length. But of course, we wanted a strong coupling where you would have expected a black hole. And once you have the coupling where you expected a black hole, you find the size of the bound state, if you try to estimate it, the diameter of the bound state, it actually grows with the number of branes and the coupling. And in fact, a rough estimate showed, at least for the simple model of D1, D5P holes, that Strominger and Buffer started, and the near extremal version was done by Callan Maldacena, and then for so many versions of that. But for all of those cases, if you're making a rough estimate, doesn't matter which case you take, you find the size of the bound state is always of the order of horizon size. And because there's so many parameters in it, the sizes of compactifications, coupling, alpha prime, numbers of branes, the fact they all fell into exactly the right place to reproduce the size of the horizon, I think that's very curious, and one should definitely.
Samir, I think there's a couple of questions from the chat and everything else. Can we just pause for a second? Are there questions?
Yes, let me just pause. I can't see the chat. Would the people like to ask the questions?
So can I just ask?
Yes, please.
Go ahead. Yeah.
Okay. So
same rules as last time.
In the previous, yes, in the previous slide, when you mentioned the infinite number of states inside a black hole, are you saying that Are you saying also that the Bekenstein entropy is not the actual, the correct way to count the number of states in a black hole?
That's exactly what this is equivalent to, right? If you see an infinite number of states, and then if somebody else comes and says, no, I think Beckstein entropy actually measures the number of states I could have in the whole, those two are in conflict with each other. That's exactly what I was saying. If you're willing to say that the Beckstein entropy doesn't actually tell you how many states there are inside, and you can have an arbitrary number of states inside, then you don't have a problem. But that situation is called the remnant scenario or the baby universe scenario.
But this is just the mere fact that you can have negative energy particles inside a black hole. Do you agree that this alone allows? This alone breaks the Bekenstein's law, because you have negative energy particle, you decrease the area and increase the number of states. So even with 5 negative energy particles, then this is still correct.
I didn't catch the last part. Can you repeat the last line?
I just mean you break the Bekenstein's law, not only with infinite number of states, but even if you have 5 negative energy particles, they will increase the entropy while decreasing the area.
Well, okay, so I had to think a little bit about that, because the Bekenstein law just says that in this volume I can't put more than so many states, right? If you put 5 negative states, and you can't actually do it if you start with 0 area, right? First, some positive mass inside here, which I haven't drawn, which started to make the black hole. Maybe I had on some earlier slide, like here, the initial matter which made the black hole. I need that to create the horizon first, right? And then I start putting all these partners in there. So the total mass is always positive. That's the positive energy theorem. And even in semi-classical gravity, nobody has argued that you can violate the positive energy theorem. So you still have total mass positive. And it's also important you have an infinite volume here, because otherwise you could say if you pile all those particles on top of each other, then if they are bosons, they'll only make one state. If they are fermions, you can't pile them on top of each other. So the infinite volume and the negative energy, it's all relevant in there.
Sorry, I don't understand the infinite volume part, because, say you have a black hole with mass m, of course, a large mass, and then the area is proportional to m squared, and then you add 10 negative energy particles to that black hole. Those particles, those negative energy particles, will increase the entropy. They will increase the number of states inside and decrease the area. Do you agree?
That is all true.
Mm-hmm.
That's all true.
Yeah. Okay. Good.
I think we should probably hold that question for the end and let Samir move on.
Thank you.
Okay, so I was just here at the Fuzzball paradigm. There were some rough estimates in the earlier years which showed that the size of bound states just never becomes small, and that suggested that, well, if you go and look at the states one by one, maybe you should find that they never actually make a horizon, and then everything is like a piece of coal or a planet or a star. Just get a string star rather than a black hole, and then the puzzle goes away. And so that's basically what happened when people went about looking for these states one by one. Then you found that, in fact, no state anybody has been able to make actually has a smooth traditional horizon. You just actually get something more like a piece of coal. So just technically, if you try to make a ball-shaped region around the horizon, the traditional hole, if it's a 3-kilometer hole, I can make a ball-shaped region of 10 meters, let's say, in which the state is the local vacuum up to some small correction. And then you automatically get this production of entangled pairs. Again, you can say there will be small corrections from some quantum gravity effects, but that doesn't happen for the Fuzzball. There's no horizon where the light cones have turned over. You never see a closed-type surface. So it just radiates from a surface like a piece of coal. There's no entangled pairs. And so there is no puzzle. It's just the same as a piece of coal. So there's so many cases now made with these Fuzzballs. I don't think there's any chance that one can actually find a whole large category of states and say, no, these were really had smooth horizons. I think all kinds of different limits have been tried. And at least for me, I feel convinced that everything basically in string theory is a Fuzzball. And so with that, it seems the puzzle is over. So if that's what we have understood and the black hole puzzle is over in this manner, why are we still worrying about the information paradox? What is the question that we are asking? So let me try to say what I understand about what people are trying to worry about. And that, for me, that will involve the small corrections theorem. So let me actually just go to talk a little bit about that first. And what the small correction theorem will tell us is that if you don't want to have the Fuzzball resolution of the paradox, that you can still have smooth horizons in some approximation, then you will really have to have non-locality. So I won't actually derive the small correction theorem here. That, of course, there are many other talks I've given on that. I'll just actually put it in the context that's going to be relevant for our discussion. And so what we'll do is we'll look at a scenario which is very tempting, that you would like to have such a scenario, but which is what does not work when you take into account the small correction theorem. Okay, so just look at all the inputs I'm putting into this thing and see which ones of those you like. So step A, let's say the exact description of the black hole is some very complicated string theory dynamics or some quantum theory of gravity dynamics in the entire region of the black hole, say going up to r equals 4m. Okay, so I will give you some region outside 2m, up to some region in the region of the black hole, 4m, 6m, whatever you want. There's some complicated quantum gravity dynamics. All we assume is the dynamics here is unitary. And then far from the hole, let's say after 100m or any number you want to put, let's say physics is normal local flat space string theory, which you can pick up from a text like Green, Schwartz, Witten, or Polchinski. There's nothing new going on there, just ordinary physics, string theory around gently curved space, textbook physics. Okay. And then suppose you want something more though. What you want is that somehow out of these complicated gravitational degrees of freedom, some complicated combinations, and we won't even bother to specify which combinations, they behave like semi-classical degrees of freedom. So it is somehow possible to extract a semi-classical effective dynamics. I will try to keep, whenever I use the word exact, I'll put it in black. And whenever I use a semi-classical, that's the semi-classical extraction of that, some approximate degrees of freedom, I'll try to put it in red. So these approximate degrees of freedom, they're like, let's say a scalar field satisfies box phi equals 0, and phi is like a scalar field, and these are the approximate quanta, and these are the ones that will look like the semi-classical dynamics of the black hole. So what we are saying here is there is an exact dynamics, and then there's a semi-classical dynamics here also. Now, if you get a semi-classical dynamics, then you can't avoid the pair equation. So that we know that's just the semi-classical dynamics. So you get the modes will stretch, and you will get the pair of the semi-classical modes, which will be 0, 0 plus 1, 1 plus order epsilon. I should have put this in red. This is the semi-classical part that we have gotten here. Okay. So now, and we'll be very generous about this. So we'll actually ask for this effective field theory, this red color description, semi-classical description, to only work for low energy modes, like wave that's bigger than 1 Fermi, let's say from the nuclear scale to 3 kilometers, the scales where we really understand physics, not anything like Planck scale or anything. We'll even argue that the dynamics box phi equals 0 needs to be only reproduced up to some approximation. Let's say some corrections epsilon much less than 1, let's say to 1% accuracy, or if the mass of the whole is m to 1 over m accuracy, but doesn't have to even be exact. And we don't even assume this map works for all times. The semi-classical approximate map we are making, it should just be enough to reproduce a space-time region. It should work in a space-time region of size, let's say 20m, so that it allows us to follow the emission of a few Hawking modes, let's say 5 or 6 pairs. Otherwise, we can't even use it for the information puzzle. But after that, it's possible we have to use a new set of, a new map from the complicated degrees of freedom to the effective degrees of freedom. But at least for a few pairs, we should be able to follow it. So this would look like a very generous set of conditions we have given. It might look that some complicated combination of the effective degrees of freedom will actually allow this kind of a semi-classical description. If we could have that, then the semi-classical intuition would also be reproduced, and maybe the fuzzballs could also be right. But then in this situation, with what we have assumed, the following is forced upon us. In the exact description, some complicated blob of these complicated degrees of freedom will leave that messy region and try to head out. That's the quanta, which in the semi-classical description is giving rise to this B and C entangled quanta. And then this is the important step. Once you go to infinity, because we have said that infinity is a normal place, there's nothing funny happening over there. In the exact gravity theory, of course, it just became gravitons. But whatever approximation I was making out of all these complicated degrees of freedom, once I get to infinity, whatever was coming out of there, again has to be just like gravitons. So there's one person in the full exact computer, which had the whole string theory in it, was doing the exact calculation. And his student was following along, let's say, an approximate calculation in the semi-classical description. But when you get to each of the description near infinity, this will give you the exact state of the gravitons at infinity. And this gives you at least the same thing, because he's trying to follow the same thing down by approximations, at least up to some small corrections. It has to be the same state as the other person got. Well, all this looks very reasonable. And all it is saying is that the exact quantum gravity mess admits a semi-classical approximation around the black hole region for small time, small meaning of the order of a few crossing times. This is where the small correction theorem will then come and tell you the following. If all this was true, then in the exact theory, and again, I already put exact in black, so we know what we are saying, the entanglement cannot come down and the page curve will keep going up. So if we wanted the exact theory to really have the entanglement coming down, if it actually admits a semi-classical approximation of the kind we just mentioned, with all the things that I just mentioned, it's not going to work out. This is not obvious because this small correction theorem uses the strong subadditivity, and so that's not an obvious result because it requires several pages of proof. But we're just using the result, and with that, it's not just requires about 10 lines of calculation. and you can prove that the entanglement will not come down. Well, so if we do want the entanglement to come down, we have to violate one of the assumptions that we had made in the theorem. And certainly if we make the physics to have non-local interactions, and again, I'm talking about the exact theory. I always want to be careful about exact and semi-classical because that, and some approximate semi-classical, because that creates a lot of confusion. If in the exact theory, I actually allow myself some non-local interactions between the regions at infinity and the regions which are this complicated region of the black hole, then of course the argument, the postulates of the theorem do not apply, and you can bring the whole page curve down. So I think this is very important for me because the way I think about the fuzzballs, we won't actually have this. So the situation will be that there are two sharply different possibilities that you are left with after the small correction theorem. In the fuzzball paradigm, you just have like a piece of coal, and there's no semi-classical description possible at the horizon, even for the emission of a few quanta. Once the quanta leave, they just go like from a piece of paper. Once a photon is emitted, it doesn't change its spin further. So you can ignore all interactions, the guy is just going. So here, the whole difficulty of the fuzzball paradigm was to actually show that in the actual theory of quantum gravity, the no-head theorem is broken, and you actually get the states, which is the kind of work that, Bina, Warner, Martinek, Turnow, Justo, Rob, all these, a lot of people are, Shigemori, all these people have been doing these very complicated calculations, making all these kinds of states explicitly and seeing what you get. And there's a nice paper of Gibbons and Warner, which shows why the no-hair theorems actually break down with all the stuff that you have in string theory. But for this, you have to use the exact string theory, because if you left me with just 2D gravity or 3+1 canonically quantized gravity, I don't have any fuzzballs. Okay? So the difficulty here moves to actually showing there are fuzzballs, but after you have fuzzballs, there's nothing else. Actually, there's nothing else you can even do because there's no semi-classical approximation. You can ask other questions like properties of fuzzballs, what they mean for cosmology, which I think are very interesting questions to study, which is what I think we should be doing. At least that's what I'm doing. But there's nothing else for the information paradox here. Story is over. But now suppose you do want to, this is the other possibility, suppose you do want to have this semi-classical description available at least for a few pairs, then the exact theory must have some kind of non-locality. It can't really be like a piece of burning paper. And we saw in Juan's talk what this kind of interaction might be. But I just want to always be careful to put the exact theory things in black and always say, the word exact very, very precisely, so that we know that we are, when we are talking about approximate things and when we go back to the full theory. Okay, so that's what the small correction theorem tells us. And let's see, in this context, what do I think the wormhole paradigm is trying to say? So from what I understand, the origins of the wormhole idea lie with the eternal black hole. And this goes back to old work of Israel, who looked at a two-sided black hole, and then Juan's papers from 2000, 2001, and then Van Ramsdonk gravity essay at some point. So here the idea was, if you take two entangled CFTs, they're entangled in this state, but they're not interacting. Then what is the dual? And the postulate was the dual would be this kind of a geometry, the eternal black hole geometry, which, however, is connected as a manifold. It's connected on the two sides. And so somehow, if you have two theories which on the CFT side are entangled but not physically connected, there's no interaction happening between them, their dual can still have some kind of physical interactions. So when I first saw this, actually, I was very excited. It looked pretty beautiful to me. And I spent about a year playing with this and, telling everybody I'm very excited about this. But ultimately, after a year or two, I found that I think it's not correct. So I think it's important for me to say this here because my differences with the whole wormhole paradigm sort of start here. And so I think that this thing is not true. And so I think if you just take two entangled CFTs, each CFT state is just a fuzzball. It's like, something just caps off here. And the other guy just some other fuzzball just caps off here. And you can, of course, you get an entanglement of two things like this. And okay, you can always entangle two things, so you get linear sum of them. But there is no way in which you can actually represent that by this particular geometry for any purpose. So you might say, well, it's a representation. So, this it may be approximated by this for some purpose. So then you can say, okay, but what is the purpose? So I'll make my statement more precise. If you actually want to consider the information paradox, for which we are looking at the dynamics of E of the order of T quanta, energy of the order of the temperature, right? Not, let's say, some high energy probe or something. If you're looking for energy of the order of T quanta, anything to do with the information problem, whatever intuition you get once you make this picture is not correct. You actually stop here, and you have to stop with the fuzzball story, and you can't actually go here. And one way to see what I'm saying here, just a second, was there a question for me?
Yeah. So in your opinion, what's wrong with the original Maldacena argument that you're just taking the torus and you're slicing it and then gluing some? So if I remember correctly, the CFT was defined on the torus, and he had some particular slicing of the torus with some dual geometry, and then he would continue it and get this picture. What do you see wrong with that picture? With that?
Yeah, so I think for me, it's very interesting because I think your question can be asked in the following way. And I have a paper about this from 2014, and maybe I'll refer you to that for, it's just called What's the Dual of Two Entangled CFTs. So for more details, I'll refer you to that. But it's very interesting to ask your question in the following language. Suppose you start in reverse. Suppose somebody gives you the eternal hole and say, what's the dual to that? And then you seem to go exactly the direction that Juan went, right? Because then you say, what's the dual of this? The dual must be something at the boundary, and the boundaries are two disconnected pieces. So what choice do I have but to end up here? And I think the answer to that question is that the eternal black hole is not an allowed geometry. But when you have all these other fuzzball solutions, what happens is when you try to make this particular geometry, which has this, horizon, smooth horizon and everything, the fact that all these other fuzzball states exist, they actually destabilize this geometry in a way that I have tried to explain in my recent papers on the retro hypothesis, and they actually don't allow you to have this. So in a time much shorter than crossing time, this will just break up into this. This is not a good eigenstate anymore. If you have some particular geometry you write down, but there are too many other states which have the same energy which are close to it, then the geometry the wave function just spreads over those states very quickly. That's a very crude way of putting what I really wanted to say. And this is not actually a smooth eigenstate. And so it's a very important question, because I really have to say that this geometry or the initial conditions you get by starting with this slice are not good initial conditions. And that's the same question as saying, why can't you make the bags of gold slice that look like a very good, smooth, long slice with all kinds of, smooth quanta on it, positive, negative energy? If I start with that slice, I've already put more entropy than S back on something. Why can't you take that as an initial condition? So I have to go and answer all these questions, right? Why isn't a bag of gold slice not an allowed initial condition? Why is the eternal black hole not an okay geometry to have starting with this slice? And indeed, in our discussion session, we can talk exactly about that. But my answer right now would be, you can't have this geometry because the fuzzball destabilized.
I just wanted to make also a comment. So maybe you could have both pictures being correct. There was a paper by Jaffaris and somebody else recently.
So I would say no. So I would not be agreeing with that. In fact, in this 2014 paper I refer to, I'm talking about what kind of non-localities and wormholes you would need if you want this picture to be right, this kind of picture. And then in the end, I'm going to say that I don't believe those wormholes are there. Okay, so somebody could try to argue that, but I'm just giving you my belief for the moment. So, and the reasons I put in there, but it's still possible. Somebody could argue that it's possible that you have a complete alternative to the fuzzballs, and all through this talk I'll be keeping both the alternatives there and just trying to distinguish them. So in fact, the title of my talk is contrasting the two proposals. So we'll just look at what are the difficulties if you have that.
Question?
Yes, please.
Then how do you explain that the correlators, two-side correlators, can be calculated in both pictures from the boundary and from the bulk?
Yeah, that's an interesting point. I went back and looked at many of these papers computing just like the Hartman Maldacena thing on some entanglement and many two-point correlators. And I actually find the following, that those calculations are such that if you actually compute the correlator in the Euclidean section and you analytically continue that to the Lorentzian section, you will get the same answer. So what is happening is that most of these correlators are correlators which are actually computed in the Euclidean geometry, which doesn't have any horizon or anything. And if you look at any correlator which is an analytical continuation of what you get from the Euclidean geometry, so you compute the Euclidean geometry just like a cigar, there's a well-defined answer there. And if you analytically continue that on the Lorentzian side, you end up here. On the gravity side, you end up here. So if two things match the Euclidean side between the CFT and the gravity, and I agree that they should, then analytical continuations are going to match. So I think what you really have to look to see if the picture is wrong is something which doesn't actually have that kind of analytic continuation. And this paper I'm talking about from 2014, I wish I'd put the reference in here, but that paper, what it actually did was look at those processes which are not there in the Euclidean section. And those are exactly the pair creation processes, because the Euclidean cigar geometry doesn't have the pair creation which you get from the Lorentzian geometry. And when you look at the pair creation, you find you run into contradictions. And it is those contradictions which I tried to explain in that paper. But if you look at things which can be computed in the Euclidean section and then analytically continued, those things will obviously have to match on the two sides. So they're matching for what I would call the wrong reason, but you can't see it from there.
But I would say there are other type of calculation which will also match that evolve directly in the Lorentzian calculation. For example, you can deform the evolution in the Lorentzian time. Then you can make prediction from two sides and they also match. Like, for example, those eternal traversable wormholes that you can, like, from the boundary point of view, you can predict what state looks like, and it matches with the right-hand side with the semi-classical gravity picture.
Okay, it's a good question. And why don't we actually take those calculations one by one and then talk about them, maybe offline or in the discussion session, because it depends on which one it is. But let me just make a generic point before moving on from this, that if you look at correlators, which are, some high energy operator or some operator which is, measuring something fairly coarse-grained, it's going to work regardless of what you do. The important issue is, as I was saying before, we are looking at the dynamics of Hawking radiation because we are here today to talk about the page curve and the information paradox. It's the E of the order of T quanta and their dynamics. That's what you cannot actually use the connected picture for. That's what we are actually talking about, because you can always, this whole thing which I try to always keep working on called Fuzzball complementarity, that if you look at the dynamics of probes of energy much bigger than the temperature, then you can use an effective picture with an effective horizon for short times for doing some coarse-grained measurements. But that's completely different. It has nothing to do with the information puzzle, because for E of the order of T quanta, where the puzzle is, the Fuzzball paradigm says you cannot have this because the small correction theorem will catch you. So it depends very much on what you are computing. And let's take that up again in the discussion session. So maybe I can just move on.
Yeah, sure. Thank you.
So just to pose a question, which I'll maybe want Juan and others to think about. Here's a case where I think about things which look like fairly easy things for me to consider. Just take the two-charge extremal black hole. Okay, so this is a very simple system which has been solved left and right. We know the microstates, and Juan himself made some of those microstates. And in the D1, D5 geometry, the safety description, this is sitting in flat space. This just means it's the flat space part of it, gentle curvature, then some branes here. And I can take two sets of these systems. One I keep here, and 1,000,000 kilometers away, I keep some other D1, D5 branes here. And these ones create, in the gravity description, these solutions which we know very well. Let's say they are a meter across, and these ones also make something which, let's say, are a meter across. So here we know everything about a CFT side, we know everything about the gravity side, and the two-charge black hole. Okay, it's not a great black hole. It's extremal. It's like on the borderline of being a black hole, but it has all the same kind of features because the entropy goes like product of N1 and 5. Three-charge goes like N1 and 5 NP. So I always think, at least so far, I've always found that any intuition I have for the two-charge extremal has carried on to other cases. So let me just take this here for now. And then the question would be, for me, I just take a look at these D-branes. I can look at them in the D-brane language. They're just ordinary D-branes. Just take 1,000 D-branes here, 1,000 D-branes here. I can look at an entangled state if I want of these D-branes. And I just get entangled state of two pieces of coal. And I look at them in the gravity picture, and I know exactly what these guys look like. They're just some gravity mess. They also look like pieces of coal. And I just get two pieces of coal again in the gravity picture, which are also entangled with each other. I don't see anything extra. And so that's the sense in which I was trying to draw the pictures before. One CFT has its own stuff, another one has its own stuff. If you keep them far away from each other, I don't see anything else. And so what I'm trying to understand is there supposed to be anything else? Like I've taken an entangled state of these two CFTs. We just take some state, tensor some state, and superimpose with that some other state, tensor some other state. Is there some kind of physics I'm expecting here, which is some string theory physics, which will give me some kind of a wormhole in there? Again, I've drawn this in black because I'm asking, is there some thing in the exact string theory, which I'm supposed to see here? Anything in black is supposed to be exact. Given what I know about string theory, like strings, branes, everything, am I supposed to see here? So it's more like a question for the wormhole people, but I'll just say that I don't think there's anything here. And if there's supposed to be something here in this exact picture, I would like to know. Maybe they're not supposed to be, but I thought that they would have to be here. Okay, so now I just want to talk a bit about my difficulties with the computations I've been reading, which motivate the wormhole picture. But just before that, let me just put in this warning. The comments in this section are on things that are the work of other people. I don't work on this. So let me apologize in advance for any errors I'm making in representing what they are saying. And they should tell me now offline if I'm misquoting anything. And so these comments should really be taken as a starting point for a more detailed interaction to resolve these issues. I'm just putting down here what I have understood by looking at these papers over the last 1.5 years. Okay, so first, as Juan already said, Euclidean computations are Euclidean computations, and the difficulty with them always is, where are the states that cause the information paradox? The information paradox came because in the Lorentzian picture, we can make this slice here, which is infinitely long, and we can hold an infinite number of states there, and that's the origin of the problem. But in the Euclidean geometry, you only have a cigar whose geometry closes outside the horizon, just closes at the horizon. So actually, you can't make the infinite number of states. And so if you look at a Euclidean computation of the Gibbons-Hawking entropy, you always get a finite answer. So you can take the cigar geometry of the Euclidean cigar, you can add handles to that. That will give you whatever computation does. So you're in principle allowed to do that, even though Gibbons-Hawking didn't do that. Let's do all this, Euclidean calculation, including all handles, but it'll still give you some kind of an answer. If you extract an S-Bekenstein from that, you'll always get a finite answer. So if you were to say that, because if we say if somebody were to say the Gibbons-Hawking answer is already the correct answer for the entropy, well, then there wouldn't be any paradox, right? Because the paradox is the fact that in the Lorentzian section, we can actually get an infinite number of states explicitly in front of our eyes. So the information paradox can be restated as the mismatch between the Euclidean answer and the actual infinite number of states you can see in the Lorentzian code. So Juan has already been Yes, please. Just one second. Let me just finish that statement. So Juan has always said that no, if you don't like Gibbons-Hawking, you won't like, whatever he's doing with Euclidean. And thank you for that comment. And so there we may be on the same page. But I just want to explain here why I don't like Gibbons-Hawking and why I think I'll have to move on to the Lorentzian sections and not draw too much from the Euclidean ones. So yeah, let me take your question, please.
Okay, thank you. So here in such a picture, you are assuming you have like an infinite number of negative energy particles inside, right?
In this,
and this and those
that's what I was drawing here.
Yeah, and those negative energy particles can only be inside if they have a partner with a positive energy outside. So you are also assuming an infinite number of positive energy radiation outside.
No, so that's not true. You don't need these guys at all. You don't need these guys. So that's the bag of gold way of putting it, right? You just have this long slice. You can put
understand Hawking particles are created in pairs, right?
Sorry again.
I mean, Hawking particles are created in pairs.
So if you create them by the Hawking process, yes, you will have the outside radiation quanta also. But once you draw this geometry, you don't have to act, because you can always give on an initial Cauchy slice any data that is allowed by the gravitational constraints. You can start the problem here. You can say, I'll take this as my Cauchy slice, and then on that Cauchy slice, I'm going to put these particles. Let me not even put these outside guys. I'll just put these particles. And that's a completely good data, creating this geometry of mass m with an infinite amount of entropy. So the way the bags of gold problem is postulated is posited. The way you make the problem, you don't have to take the outside radiation, but you could. It doesn't make any difference. Okay, so this is what I was saying just now. If you are allowed to say that,
can I ask a question as well?
Yeah, just a question for me.
Yeah, sorry. I'm just I'm not totally comfortable with the way you characterized the Gibbons-Hawking calculation as a Euclidean one, as opposed to the Lorentzian one, which would expose the information paradox. I mean, would you agree with me that the Gibbons-Hawking calculation is an answer to the question, what is the entropy of the thermal state? So I put the system at a temperature, and in that case we expect the entropy to be large, and it's remarkable that doing a path integral calculation with a saddle point approximation in gravity gives you a finite and definite answer. This would not happen in a non-gravitational theory, and we think it's probably the right answer, but I don't think it's so I don't think it's the wrong answer in any sense. If you believe that information comes out in a process where a black hole was formed from a pure state, then that's just not the calculation you should do.
No, absolutely. But I think that is exactly where people sometimes are going in a circle. We all want this to be the right answer. We also believe it's the right answer. The paradox is exactly the mismatch between this and this. So unless somebody can actually, so what the Gibbons-Hawking saddle point shows, what you get by this calculation, you compute the action, you do this, you get some finite answer. It has never been clear what it means, right? So the whole problem was people did the calculation, they got an answer, The answer even agreed with the fact if you have a temperature T, which you get from Hawking radiation, and you use TdS equals dE, you get the same answer. That's the answer we would all like to believe. If you say, but that's the answer, and so this answer is just wrong, instead of answering the paradox, you have run away from the paradox. Because the paradox is the fact that you can make this till you go back and address why you can't make this. Looking at this hasn't brought you anywhere closer to the paradox. You are restating the paradox and not solving it. So I'm glad you asked that, because I really wanted to be very clear about that if anybody says, I have the Euclidean answer, I have gotten something I like, let me move on, he hasn't even started. The information paradox is the fact that the Euclidean answer always gives a finite answer, which agrees with everything we want. The paradox is that's not the Lorentzian answer. So
I guess I disagree with the framing of the problem. So I kind of agree with you, but the paradox is, in my view, and I think in yours as well, the tension between having information come out to a distant observer and having no structure at the horizon for an infalling observer.
Agreed, absolutely.
Whereas what these calculations, such as Gibbons-Hawking and the new calculation involving islands do, are direct computations of the entropy in particular states, different states. So Gibbons-Hawking was a thermal state. In the recent case, it's a pure state, but they're direct computations of the entropy using the gravitational path integral. And it's just remarkable that you can get the right answer, or what we think is the right answer, from that calculation. It doesn't change the fact that this answer, indicates that we have a unitary theory, and we then have to worry about structure at the horizon. I think in both cases, that's the direction that the answer goes into, because Gibbons and Hawking had no right to find a finite entropy, and similarly, this is just a new, more sophisticated way of computing an entropy in the case where the black hole was formed from a pure state.
Yeah, so thanks for that question, because what I'm going to do in these remaining slides is exactly go into various papers I have been reading about the kind of calculations you are mentioning. And what I find is that those calculations, so I'll try to talk about my difficulties with those calculations, and then maybe at that point you could say, where I'm making a mistake in understanding those calculations. But I'm finding that those calculations are not showing a page curve that comes down. So let me just get to that, and then I think maybe in the question and discussion.
Can I just make an organizational thing? I'm really happy for everybody to discuss the constructions on this, but I'd like Samir to have the opportunity to present his case, and then we'll have a free-for-all with the panels and the follow-up discussions. But let Samir present his case and what he believes, and certainly ask questions for quick clarifications. But let's just.
I have a quick clarification question. Sorry, I got a bit confused. So, are you claiming? So you're claiming that the Lorentzian hole has an infinite number of states? Is that right?
Absolutely. The Lorentzian hole.
And are you claiming that that's supposed to be the correct answer?
No, of course not. So the semi-classical picture here has given us an infinite number of states. I think that is clear to everybody.
That's clearly wrong, right? Yeah.
What the small correction theorem shows you is that if you want a smooth horizon, okay, then this semi-classical picture cannot be avoided. If you actually have a smooth horizon, you cannot solve the problem. And so the whole debate is about the smoothness of the horizon. If you agree that the horizon is not going to be smooth in any approximation, you are already in the Fuzzball paradigm, the story is over. But the
what's the problem then with the Euclidean computation, which gives you a nice finite answer?
So that is
apart from the fact that it uses the NLP continuation of a smooth horizon.
So if you take this particular Euclidean answer and you find a finite answer, if you analytically continue this to the Lorentzian section, there seems to be a mismatch because there are infinitely many states in the Lorentzian section. Normally, when you have a Euclidean calculation, I think that's what I had on my next slide or some slide. Normally, when you have a Euclidean calculation, and this is a thermal loop, if you slice the loop like this horizontally, the states running in the loop are all the states of the theory. But the trouble we have always had with Gibbons-Hawking is that if you slice this thing here and see what's running around, you don't see the states which you can actually make in the Lorentzian calculation. And if you take a theory like JT gravity or 3+1 canonically quantized gravity, I think the mismatch is real. It's not like there is any small correction which will fix the mismatch. The Lorentzian theory and the Euclidean theory are just giving different answers. The theory actually has an internal problem. What's going to happen in string theory is that the actual states which run in this loop will be fuzzballs, but they will not have a smooth horizon. with them being fuzzballs, the one loop saddle point, one loop path integral on them, which are actually made of states which are not these states, but which are actual fuzzballs, those running in this particular loop, that path integral is now well defined. That path integral has a saddle point, and then that saddle point will be this. I'm not proving that. I'm just giving you my picture of what the fuzzballs are doing. But the Lorentzian picture here is the one that has the problem. But let me just move on because I'll run out of time. So as I said before, if you are to assume the answer that this is the correct answer, then there'll be no puzzle in the beginning, because as the whole evaporates, the area goes to 0. Then the entanglement will have to go to 0 because you can't entangle with more states than you have. And so then we would have had no puzzle from the beginning. And so one of my difficulties is that I'm going to find later on, after I show you what my difficulties are with many of the current calculations, they seem to be actually be just saying this. And so as I said before, in the Euclidean calculation, you don't actually see the states that you have. And so the mismatch between Euclidean and Lorentzian was the paradox. But that's fine for the moment. Let's forget the Euclidean and just notice the fact that the page curve is actually only defined in the Lorentzian section, because you have to actually look at emissions. It's something plotted as a function of time or as a function of emission steps. So we really should go back to the Lorentzian. The Euclidean thing suggests something. That's very good. We should use that. We can use that. But in the end, we have to see what to suggest for the Lorentzian. So I want to go back to the Lorentzian and see, what they have supposed to have told me. Just the Euclidean, if I just say Euclidean gave me a finite answer, well, that time it was for the entropy and Gibbs-Hawking time. Now it might be for an entanglement entropy. I can't use it anyway because that is the mismatch. So let me go to what I was trying to learn about Lorentzian from various papers. And again, I apologize if I'm misquoting anybody, but this is what I understood. So first I tried to read some of these papers, which one of these papers tried to establish a picture where you do have a black hole horizon, but somewhere behind that is an end of the world EOW brane, which can have lots of different flavors. Each one of them could be labeled by some state psi I. And I was happy with this because from what I understand, each of these different flavors of the brane could model as a rough way one of the possible large number of states that could have on the long slides inside the black hole. And these states I are the states of the radiation. And if I take that interpretation of what was going on in this paper, then a state which has the inside entangled with the radiation would look like this. State of the radiation, the corresponding state inside, and then you just make the entanglement. This would have been Hawking state, where each different flavor of this brane is one of those deep states deep inside the black hole, which was causing the problem. And then from that, if you compute a density matrix, there it is. And this is the dot product of psi I with psi j. And when I did that, I reached this particular section of their paper, section 2 or whatever, and I do that, and I find the entanglement is actually rising. It doesn't go down. If I keep increasing k, which is what I'm supposed to do, the page curve doesn't come down. Okay, but the paper is actually saying the page curve does come down. And so how do they do that? Because what they do is they say, no, this is supposed to be a dot product, because if from a state you go to a density matrix, then this thing is supposed to be a dot product. They should know we'll replace the inner product with a transition amplitude. So it's very important to, whenever I want to, because they want to distinguish them, we shouldn't just write the symbol, because the symbol is used both for inner products and for amplitudes in different places in quantum mechanics textbooks. But just to be very clear about it, let me say that inner product is what you really want in the original way of defining a density matrix, but a prescription is now being put in where we replace the inner product by an amplitude. But the inner product is not an amplitude, because even for theories with gravity, let's say the worldsheet theory of string theory is also a theory of 2D gravity, right? And we have done 2D gravity in many, many different contexts, like KPZ or dynamical triangulations. And inner product is something where you take a state, another state, the bra state, put them on top of each other, like with no separation, and just dot them. So the fields here are exactly the fields here. That's the states which are, have dot product 1. A transition amplitude is different. You can put one state here, one state here. You have an evolution in between. All kinds of things can happen in between. Handles can come, it can go and interact with something else. So there's no zero separation. This word is wrong here. So a transition amplitude is not an inner product. So why are we making this replacement? But well, let's assume it's their theory. So let them make the replacement. And the moment they do that, they find that the amplitude, if you normalize that to be delta ij, then the square of that amplitude is not delta ij. And that, of course, by itself doesn't make sense, because square of 1 or 0 is always 1 or 0. And then they get out of that by saying that we are acting in ensemble average theory. So these are not numbers, but ensemble averages. And so if you want to start a normal theory like string theory, I think this is not that. I think that's what the conclusion at that point was. So then we don't seem to be addressing the original problem. So I don't know what this prescription would mean here, but let me just take it for now and say, let's follow this modified inner products, where you replace these dot products by amplitudes a little further, because right now I seem to be in a different theory. I can't even go back to my original theory, but there are other papers which don't emphasize that part. And so let me see if I can go and say what are my troubles with this inner product to amplitude kind of replacement. So
sorry, I don't think
there was a question for me. Just 1 second. Yes.
Okay. Yeah. I don't think we write it as amplitude in the paper. We just say it's the inner product. But when calculating the square of the inner product, there's the wormhole contributions. Why you say we replace it as an amplitude? There's no time evolution between these two states.
Good. So if you have, so what I saw drawn there, which is why I called it as an amplitude, maybe that word, if that's not the correct word, I apologize. If you have two states like this here and here, if you can do other things, like if I have a 4-string diagram, like two brass strings and 2 ket strings, in a dot product, I would just join them as they are. That's the way I would do inner product of states in string theory. I could have 2 strings and I have some way of taking the dot product. But if I allow things like connected diagrams between them, that is not what I do when I take dot products in string theory. That picture looks like a string amplitude. So if you look at just string theory, the theory of gravity, right? It's the worldsheet 2D gravity with scalar fields. This exon can be called scalar fields. There's a well-defined notion of dot product on the Hilbert space of 2 strings. And that is not the picture that I saw in the papers I was reading on this, because the pictures I see there are the ones where you actually have something more like an amplitude. So if you had another pair of strings here, you're allowed to actually connect them with each other. That's what I was trying to show here. So whatever it is, it's not the original dot product. Is that fair to say for the moment? It's not the original dot product, and we can still call it a modified dot product for the moment. And
yeah, you can call it a modified
inner product. Okay. So let's go with modified inner product and see what
practical
happens.
points, Samir. You've got about 8 minutes, and we'll throw it open for 5 minutes of questions. Is that going to be good enough, or do you need a bit more time?
I think that's fine. I'll try to end in 8 minutes.
8 to 10 minutes. Okay.
Okay. So let me not try to answer any more questions for now, but let me just try to get to the end and then take the questions later. Okay. So then I went and looked at some papers of Mathur and Maxfield. Okay. So they are long papers to read. So I'll just tell you what I extracted from them. At first, I was very happy to see this paper because they said here is infinity, and infinity is a normal place. There's no non-local effect from here to here. So I said, okay, that's something I can relate to. I can live with that. And they want to compute Rényi entropies. And for that, you need to compute things like trace rho to the n for some density matrix rho. And so let's compute trace rho square. So you take 2 copies of a state and the 2 copies of a state. These make a reduced density matrix when you trace out the interior. Let's call that rho r. Trace out, same thing here, trace this out, call it rho r. And then let's see if we can compute trace rho square and learn something interesting. Okay, it's the kind of setup you would like, because at least I would like, because nothing funny is happening at infinity and we are computing trace rho square. If you use it using normal inner products, the way I would have done inner products in a theory of gravity, I find that the page curve doesn't come down. Okay, they say it'll come down, but I don't find it to come down. So let's dig in to see why they're saying it comes down. Well, as we said, they're going to change the inner product in the interior, and they say this will bring it down. So let's see what they actually do. But before you do that, you go and see where in their paper do they say that they are actually using a smooth horizon. So you find it's nowhere there. So in fact, you could equally well have pieces of coal here. Now, if you had pieces of coal, the page curve should come down. And if you actually do the calculation of this page, this rho r, and then compute rho r square for a piece of coal, for a normal statistical system, there's a nice paper of Liu and Worthen. If you look at section 2 of their paper, they show you how for a piece of coal, you'll have 2 different saddle points changing roles at some point, and the page curve actually comes down. And you say, okay, that's good. So at least for that case, I know how it works. But if you look at the Liu-Worthen computation, it requires what you think you would require. You need a bounded Hilbert space. That's the total number of bits here cannot actually increase. It doesn't actually allow you to have the pair creation. If you go to section 3, they start talking about black holes, but actually I don't agree with that section of the paper. But I think section 2 is really beautiful. They show how the different saddle points for a piece of coal will show you that the page curve comes down. But here what I'm complaining about is the fact that in the Mathur-Maxfield paper, they are nowhere using the fact that they actually have a smooth horizon, which has pair creation. Okay, so let's go and put in the pair creation into the Mathur-Maxfield papers and see what happens. Let's put in the fact that they have a smooth horizon. And so now I have pair creation there. And now I should be finding my original problem. Nothing is being moving out to infinity. Infinity is a normal place. I am creating pairs. These partners are going in. I should be having my problem. I've really zeroed on to where the problem is. So how come they are saying the page curve comes down? And then I go and see what are they getting with their new inner product. Let's see what's this modified inner product. It goes in the following way. If I have 2 copies, I and j, of something, and then these are the 2 kets, these are the brass, these are the kets. A normal dot product would be delta I prime, delta j prime, And if I put that in, I would get what I was calling my correct dot product, which would give me a rising page curve. That's not what we want. So let's change the page curve so that it actually becomes symmetric. You not only have delta I prime, delta j prime, but you also have it written the other way. Okay, so let's see what the dot product is. Let I and j only be two possibilities, 1 and 2. And then, okay, I should have called them 0 and 1. So then there are 4 possible states for this ij combination. They are 0, 0, 1, 1, 0, 1, 1, 0. And the original dot product, of course, was unitary. It was just identity on the 4-dimensional Hilbert space of this. But with this modified dot product, you find this dot product matrix has a 0 determinant. One state has a vanishing norm. So what's really happening is that this modified dot product, it's actually making the theory inside the black hole region non-unitary. But if you allow non-unitarity inside, that 2 states can be crushed into 1 state, of course the page curve can come down. That was Hawking's original non-unitarity, where all the states inside were crushed into 1 state, the vacuum. Also, like always, Maldacena's final state boundary conditions are sort of in that same spirit. If many states can go to 1 inside, then of course you can get the page curve to come down. But that's exactly what is loss of unitarity. I just make a few comments on this third thing and then try to put up my summary slides. Let me just talk a little bit about the QES prescription and where I run into trouble with that. From what I understand, this is the prescription. Everything inside the ADS boundary, normally we thought it was described by the CFT, but it's not described by the CFT necessarily. We choose a quantum extremal surface, which I've called QES over here, and then one extremizes the quantity, which is called generalized entropy SGen, which is the area of the surface of the QES plus the entanglement across the QES. So I define generalized entropy. And then if I take the QES and place it where this thing is extremized, and that's the location of the QES, then the CFT describes the physics of the ADS from the ADS boundary up to the QES. It could include the black hole horizon, but may not include things which are deep inside the horizon. Okay, so quanta deeper inside, they may then be described by the radiation zone, but the CFT only describes stuff up to the QES. So the QES is all the way here, the CFT describes everything. The QES is here, then the CFT only captures this part. Okay, so this way you can always get the entropy of the black hole to never be very big, because if too much stuff collects here, the QES just jumps over here, and then the black hole is described by only this part of the stuff, and so then all this is not inside the black hole. Okay, so let's see where I got into trouble in trying to understand that. First, I just took a look at this kind of state, but I make this long slice, and only I take one set of spins, let's say some combination 0, 1, 1, 0, some chain, and I put the same chain over here, 0, 1, 1, 0, but I don't entangle them. Just some particular state here, and then the same state over here, no entanglement. But I take a lot of them, okay, so a number much bigger than S Beckett's time. Okay, I'm going to entangle them later, but right now they're not entangled. Well, right away you could say 2 things, and we'll look at both of them one by one. You could say, I'm not going to allow you this long slice. You can't put more than n equal to S Beck quanta there. You just can't do this. But in that case, you are going in a circle. If you haven't even allowed me to put all these, to have this long slice where I can put all these quanta, and you haven't even given me a reason for that, then you sort of, if you don't allow me to put the quanta more than S Beck quanta, I can never entangle by more than S Beck. Page curve has to saturate S Beck. So then you're already putting in what you're proving. So for the moment, let me assume that I can actually put this particular state here, but we are going to come back to this. Okay, we'll be forced to come back to this, so I will come back to this. So for the moment, let's allow the state. And so the total state, which I've called psi I, is whatever combination of these spins there are, 0, 1, 1, 0, whatever, on the gravity side here, and then on the radiation, it's over here. There's no entanglement, so if I try to compute the QES, I find that the QES might still be here because the area is minimized what it being at 0, and there's no entanglement. So this actually minimizes everything. And so this entire stuff is all in the CFT. So the CFT captures all this. So the entire sort of everything written in the dual language, but I have the flat space and the CFT, not the flat space and the gravity. I'll call those states as psi tilde. That is some state of the CFT, and then some state of radiation. Okay, but now I've forgotten the gravity. I'll only worry about the CFT and the radiation. But if in the CFT and radiation, I just ordinary field theory. So here, if this state is allowed, then any linear superpositions of them are allowed. But if I superpose all these guys, I get back to the entangled state, which I was looking for. And that has an entanglement entropy, which is more than S Beck. So now I've gotten into trouble. This is what we were trying to avoid. I've entangled the CFT with the outside by more than S Beck. And how did I do that? I first looked at the unentangled states, found the QES for them because they didn't have entanglement was at 0. So the entire stuff on the slice was actually in the CFT. But once that is in the CFT, the linearity of quantum mechanics forces me to allow this state and forces this entanglement on me. If I try to use a QES prescription to get out of that problem by saying that once I entangle them, the QES moves out, and so the entanglement is actually smaller. I find that there's a violation of the linearity of states in the CFT. So I've gone through it a little quickly, and obviously people who do CFTs, this stuff should get back and catch me where I'm making a mistake. But let me just finish with this, and then maybe I'll
very quick comment, if I may. On the previous slide, I think you made it. One more forward. I think here you've made the assumption that the states psi I CFT are orthogonal or orthonormal or whatever you want. I think what we would say is that the states psi I are an overcomplete basis of these black hole microstates. I just wanted to put that out there.
I agree. I agree that's what you would say, and that's what I have in step A. So let's back up and start again. So this time we are going to say that this slice actually cannot store more than SBEC states. And so that could happen that you try to make the states which looked orthogonal, but there are some small changes here and there. They're not really orthogonal. Anytime you try to make more than SBEC guides, they're just not there. But here is the point. If you still want your smooth horizon, which is the only thing we are fighting about, if you don't want a smooth horizon in any approximation, fuzzballs are the end of the story. Story has been over for a long time. If you want this to a semi-classical approximation to emerge where at least for one pair at a time or a few pairs at a time, there are some approximate variables where this thing holds, you can't do this. Because then what happens is that these new bits are created, they go into this region, and the small correction theorem then tells you the entanglement entropy here will keep rising. So how did this happen? Why can't I say that these bits are all a little bit, the dot parts are a little bit different and you can't keep, the number never rises beyond SBEC? The reason you can't do that, that this new bit that came in, because it was entangled with this guy, it can't also be a linear combination of these guys. And then you run the whole small correction theorem in, and you find what is happening. The only way to get the requirement that you cannot store this many bits is to have either this or this. Either the evolution here is non-unitary, and non-unitary means exactly what I was saying in the Markov-Maxfield case. A new bit comes in, this particular bit, but then there's a crushing. Two different states are there which were orthogonal are being crushed in the evolution. I'm looking at the evolution. This new bit is coming in. It was orthogonal when it started. I can't avoid that because it's entangled with this bit. The whole entanglement of small correction theorem constrains me. And then two things which were orthogonal have to be evolved to become non-orthogonal. You can actually prove that you will actually have to have non-unitary evolution in the interior. New bits come, but then the n plus one dimensional Hilbert space is crushed down to an n dimensional Hilbert space. And with that lack of unitarity, you can always bring the page curve down. Or nobody likes non-unitarity. The other option is you have non-local transport of information outside the hole. So you can always take a bit here. You can have an escalator, and new bits come in. You don't want to have more than SBEC bits here, but this bit sort of moves out. If you allow me this wormhole, it's all fine. So this is where I think the whole stuff that I've been reading with this wormhole thing has brought me to this point where I think that what one has is a model for non-locality, which is like this kind of an escalator. Either you leave everything inside, the way Juan was saying at the end of his talk, you have a remnant which may be detached to be a baby universe, you leave the stuff there. If you want, you might be able to make complicated wormholes and interact with it, but that stuff is there. I'm talking about the exact picture now. In the exact picture, that stuff is in there. There's a baby universe, a remnant, whatever you like, it's there. This is not the fuzzball answer. It's a different answer. Or you may have the wormhole may all be traversable, and this guy may be getting spit out, but you need this non-locality. So let me just summarize by saying, what does this all mean? Maybe I could just take a couple of minutes to just summarize what I was saying. With all that we have seen in string theory, I think there's no alternative to the fuzzball paradigm. There's just no smooth horizon. And this is the lesson that has emerged by work of the entire string community, in particular, a lot of things from Juan in the early days, from gray body factors, the Maldacena mouse conical defect metrics, and the Maldacena mouse construction. Everybody has sort of, I put in what everybody has taught me in string theory, and I just come up with this picture. And this picture doesn't actually admit the semi-classical approximation. So the trouble is happening when you want this approximation in any form to exist, you need this non-locality. So are 2D gravity computations suggesting this non-locality? So I think not, because I think the Gibbons-Hawking arguments that you can't put more than area A states in a region, or Becker-Stein's argument you can't put more than that much area in a region, they were just postulate saying that you can't put more than that many states, and the information paradox was the conflict between these things and what you actually see. And the statements I see these days in the papers I read about the wormhole paradigm that the entanglement to some region should be the minimum of what you think it is, and the area. to me, they look similar. They are saying that you can't entangle some region more than the area, but I think it's still a conjecture at the same level that Bekenstein's thing was a conjecture that you can't put more than area A, and the information paradox is the conflict between that conjecture and what you can actually make in the Lorentzian section. But of course, if you could get evidence for such a conjecture, that would be real progress, right? That's not a conjecture, that's actually progress. But I think that these calculations we are seeing, they cannot give evidence for that. And the reason for that is that if you want to say in an area A, you can't hold more than exponential of A over 4G states, you've actually got to go to the quantum gravity theory, make a large number of states, and see that they are having some angles between them or something, and they're not fitting there for some region. With fuzzballs, you actually see that, right? But in these calculations with JT gravity and so on, I don't think they have the power to do that. So they can at best restate the conjecture, and the RT thing, I think, also cannot tell us anything, because with the RT kind of arguments, the fact that area comes up here, it looks very exciting, but it cannot tell you that you cannot put more than area A amount of entropy in some region, because I keep looking at this and trying to get to this postulate, and I can't make the jump. And the reason is that here, there's no black hole, there's no closed trap surface, no horizon, there's no large number of states. In fact, I'm in the vacuum in both the CFT and the gravity sides. You can put some quanta, but when you make a black hole, nobody can look at the state. You again say the black hole, the RT tells me it's the area. So you sort of put that in. And the area, and this is in the gravity side, entangled on the CFT side. So I think for all these reasons, I don't actually understand what we can actually see from the RT agreement, from which we can actually say that we have proved that on the gravity side, or coming closer to saying that you can't hold more than area A. To me, what is happening is something a little different. I think what's being argued here is not that we can prove that you can't have more than area A state somewhere. There's a desire to get a certain picture of emergent spacetime where the semi-classical approximation emerges. And then you are forced, this is just something we are getting forced into. So the real final question for me is, why do we want a semi-classical picture? So I just had some slides at the end to say, this is the philosophical question which I wanted to address. Why are we forcing ourselves to the semi-classical picture, which is enforcing all this? Why aren't we just stopping here? But I think what I'll do is I'll just stop here and not go into this right now. And then maybe in the remaining discussion session, I'll come up and...
or in your follow-up, that would be great. But I want to let other people, I've been putting people on hold for questions. So we'll have about 5 minutes of questions and then let Juan respond. But I wanted to keep it within reasonable bounds. So can I, do you want to say any last quick things, or should we just move on to questions?
No, I think we can move on to questions.
Okay. Questions, people. Oh, resounding silence.
Can I ask a question?
Go ahead. Go ahead.
About this, about the comment that you think JT gravity cannot answer the question that there's like more interior states than the black hole entropy. Yeah, I think you can, in JT gravity, you can study the effect of whether those states are really orthogonal, and it is a wormhole that allows you to find that those states are overcomplete, and then they span a small Hilbert space by A over 4G, and that calculation can be done. So I agree with you that it's a certain non-locality, but this exactly this non-locality that is captured by replica wormhole. That's a comment. Yeah.
So yeah, thank you for that comment, because I would like to discuss that maybe at leisure. It will probably have to be offline, because I look at the JT gravity and I don't find that, right? So actually I had some comments.
Right, I put it the discussion in a later paper with Ilushi and Singh about those state reconstructions. And you can
I have some comments here about what we're supposed to learn from JT gravity, but maybe I just want to mention this here, but maybe in the discussion session, I would like to show these slides.
Expand on it for a couple of minutes if you like, but then we'll move on to another question.
Okay, maybe a couple of minutes. So the recent effects to use JT gravity have used JT gravity coupled to scalar fields, and then all these replica tricks, saddle points, field continuations. And this is obviously all very confusing. So let me ask a much simpler question to all the people who do this. Suppose you take JT gravity plus scalars that you're using and put the whole thing in a computer, okay? Lorentzian theory, no Euclidean continuations. And discretize the spatial section to small segments. You can use dynamical triangulations. Anyway, you want to solve 2D gravity plus matter, the old KPZ, DDK, string worldsheet dynamics. We have solved 2D gravity in so many ways, but put the whole thing on a computer exactly. what are people really saying? I think it's good I can ask this question now, because then maybe it's a good point for Juan to maybe answer in his part of the talk. Suppose you put the whole thing in a computer, no tricks like replica or anything needed, will the page curve go up or down? Now, when CGHS and RST had computed this 2D gravity plus scalars exactly, they found the page curve keeps going up. But of course, the new point is they didn't apply this topology change, right? So let's see what is the new thing that Juan would like to put in here. So suppose you allow the CGHS just had space-like slices that went on and on, right? But now we're going to allow them to break. If you want to do a Lorentzian theory, the only topology change you can have in 1+1 gravity, you can break the slice, right? Suppose I allow it to break, but nothing non-local, but otherwise exact. We just put the whole thing in a computer. Will the page curve come down? So it's a question, okay? I'm not giving the answer. And second, if I break these segments, but I also have non-local effects, I can make the segment like bring them all the way to infinity, like brew it up here. Then will the page curve comes down? So this is the question to all those who do JT gravity. Here are my guesses. I think in situation A, the page curve will not come down. You can break this any amount you want. If you don't bring something here, the page curve won't come down. With question B, you can bring it down, but these are the non-local effects. Then you might try to say, these non-local effects are in my semi-classical theory, the exact theory doesn't have them, but no. The small correction theorem will tell you, if you do this in the semi-classical theory, in the exact theory, you will need non-local effects. Okay, so that's all I was saying, that this is where I end up with what you learned from JT gravity. If people have something different to say, I would love to hear.
Edgar, you had a question next, I think.
Yeah, I had a question, but maybe I'll just make a quick comment about what Samir just said here. So in this case, I mean, I guess since 2D gravity plus scalars is not expected to be a good UV complete theory, it's not really kind of appropriate to ask the question in this context. So the page curve type computations with wormholes in CGHS, it's expected that that is some low energy semi-classical theory, and there's some other UV complete theories, which is not this thing quantized, and that's the thing that you would want to put on a computer. And then well, at least I would say that if you'd put that thing on the computer, that full UV complete thing, then the page curve would come down. Of course, it depends on exactly how you define that full path interval. But
so I think this is exactly my problem. My problem is that all these semi-classical things that we talk about, somewhere we have to make a link about the correction between semi-classical and exact, right? If you keep saying the semi-classical thing gives us the wrong answer, but that's what I'm going to do, and the exact theory gives me the correct answer, the page curve comes down. Semi-classical gives me the answer, the page curve goes up.
So why is the semi-classical thing give the wrong answer?
We haven't said anything, right? So let's look where the link is, right? So somewhere I have been trying to say that the semi-classical degrees of freedom have to be some complicated combinations of these exact degrees of freedom, but some very complicated combination. It could be local, or in case you tell me non-local, it's non-local, but it has to be something. And I think that's the part which I'm seeing missing. You're saying with JT gravity, it won't come down, but that's not the correct answer. I agree it won't come down, and I agree it's not the correct answer, but I think you've learned nothing from that.
No, but I'm saying the question posed should not be about that theory, JT gravity plus scalars. That's just, we expect that not to be a good UV complete theory, so we shouldn't even ask the question about that theory.
Okay. But I was just saying that at some point, if we are going to use any output from that, I need to know how to connect the JT gravity plus scalars to the exact theory.
Yeah, that I completely agree.
Some effective degrees of complicated combination of the actual exact theory doesn't give me to a leading order approximation, the JT gravity guys, then the two problems are completely disconnected, and I shouldn't be doing that. But the moment I make that approximation, the small correction theorem steps in, and most of the things that people are saying are not going to work out. The only thing that's going to work out is what Juan said. You will really have a different scenario where you have baby universes and non-locality in the exact theory.
I think Andrea is next. I think then that'll be the last question until we, and Raphael, I ask you to wait until the broader discussion. So Andrea, go for it.
So I have a two-fold question, both to Samir and to Juan, about the apparent stark conflict between these two pictures, the locality with the structured horizon on one hand and the non-locality with the smooth horizon on the other hand. And the first question is about something that Samir, you said somewhere in the beginning of the talk, which is that in the island picture, you have an exact theory, and that exact theory has non-locality. And I wonder whether this is actually the case, because as Juan said, you can get the page curve, which is about the purity of the radiation, but you can't actually get the state. So in this picture, you don't have the microstates. So if this is an exact theory, one should also be able to get the microstates. So I'm not sure whether this is an exact theory that at the same level as you were talking about string theory being the exact theory for fuzzballs.
Okay, so maybe should I comment first, and then we should let Juan?
Yeah. Okay. Then the second part of the question is maybe for Juan, which is about if you now have.
Andres, let Samir respond. Save the second part of the question to after Juan speaks, and then we'll go from there. But just let Samir respond.
Yeah, so thanks for that question, because that really I wanted to summarize what I'm saying from the small correction theorem. And this slide really summarized what I was trying to say for the first half of my talk, that I do want a connection between the semi-classical calculations or the approximate calculation, or the effective calculation, the JT gravity calculation, and the exact theory. So I've been always trying to draw the exact theory on the same page as I draw the semi-classical ones in black and in red. And it's the connection between them which I have been seeing, which I have been finding to be missing in the papers, which is what is leading to me to be very confused. And so in the exact theory, if you actually want no non-local effects, again, this is the exact theory, you cannot actually get the semi-classical approximation to come out. If by semi-classical approximation, you mean what I think you should mean, that some combination of these degrees of freedom behave like these bits. Okay, so if somebody comes and says, no, you got the page curve to go up, but that's okay. That's what the semi-classical theory is, not the exact theory. Don't bother me about it. No, you can't do that, because at some point you have to tell me that these guys are effective bits coming out of these guys. At the moment you do that, I will tell you something which is forced upon you by the small correction theorem, by this picture, and I'm going to tell you it's forcing the non-localities in the exact picture. Ultimately, we only have to worry about the exact picture, because that's what we are after, right? But it's very interesting that the semi-classical picture is forcing some requirement on the exact picture. So let's not disconnect these two. And if anybody says the semi-classical picture is fine, but it gives a wrong answer, don't take it too seriously. This is the problem. For this reason, I have to take it seriously.
Okay, let's leave it on that note. We can continue in the discussion sections, but I'd like to ask Juan to come back and respond or make some remarks, and then Samir will get another. Let's try and keep it to 10 minutes, Juan, and Samir for the second bout, so we're almost half an hour behind time. But this has been great. But let's thank Samir, Juan, please. And thank you, Samir. That's been great. So Juan, you're got 15 minutes. If we can keep it to 10, and similarly, Samir, you've got 15 minutes, but if we can keep it to 10, then we might get the train almost back on time.
Sure.
Juan, are you there?
Yeah, I'm here.
Fantastic, good. Okay, yep. So over to you. If you need the 15, I don't want to bait and switch, so take the 15 and we'll just do
That's fine, that's fine. I think I'll try to do it in 10. So I'll make some comments.
I should add, I believe, just for organization thing, that the Juan and Samir exchanged a lot of discussion, so they knew pretty much what each other was going to say. At least I believe that was the plan. So go for it.
Yeah, so I'll make some comments. So first there is this issue of non-locality, right? So let me ask first a simpler question, which is, suppose you have a qubit, you form a black hole, you send in a message, right? And the message is here behind the horizon, and you're at late times. So, and you would like to extract this message, right? It's behind the horizon. Can you do some operation and extract something which is behind the horizon? And we are allowed to do arbitrarily complex operations. And it turns out that there's a very simple answer for this. We can get this by just simply evolving backwards in time. So we evolve backwards in time, so we can do anything. That anything includes evolving backwards in time, and we can get the message. So the lesson I wanted to draw here is that sometimes things that are behind horizons, we can get them. In this case, it's very simple. And this operation of evolving backwards in time is a relatively simple process. So it's, we are acting with relatively simple operations. And the main point is that when we think about complicated measurements, we need to include the space-time created by the measurement process. In this case, is this when we evolve backwards in time, there is this whole space-time that we get by evolving backwards, and that so that was one point. Now, when we are asking then about islands and non-locality, it's well, of course, we have the EPR correlations between the outside and the island. Of course, this is some form of non-locality, but I don't think that's what Samir was talking about. There is really more. There is the idea that by doing very complicated operations outside, we can access the quantum information that is inside the island. And this is supposed to be very hard to do via unitary transformation, so even harder than evolving backwards in time. That's based on this Python's large conjecture by various people. But it is the idea that very complex operations could access the island. And if you allow more, if you allow non-unity operations such as projections and so on, then it's simpler, and you can see it through replica wormholes. But the main point is that the complex operations would create very complex spacetimes, and this somehow might get the information from the island. I wanted to emphasize what the page curve does. So it computes the entropy of Hawking radiation using a gravitational formula. And it's a first principles derivation of this entropy from the gravitational path integral, and it's similar to Hawking-Bekenstein. But I should also emphasize what it doesn't do is it doesn't tell us explicitly what the microstates are, or even compute individual amplitudes for generic final states. I understand that the Fuzzball idea is a project to give an explicit gravity picture of the microstates. And it is a project that is using the black hole entropy formula as a guide for how many states to expect, for example. So in fact, this is used as a measure of success or failure of the process of some proposals, some specific proposals of geometric constructions. But I think this program should also use the insights from the computation of the entropy of Hawking radiation and page curve and so on. It is as correct as the usual Bekenstein formula, I think, and using it as a guide might guide us even better how to find the microstates. And so entropy formulas have been a guide for understanding the gravity and quantum mechanics, and we should definitely not ignore the lessons from the page curve for this endeavor. Now, I think the primary lesson of these formulas is that the interior matters, and we get the right answer after we include the details of the state in the interior. And for the thermodynamic entropy, the interior did not matter. And so it was fine to say that it doesn't exist. However, the recent developments, starting from the application of the HRT formula for a pure state black hole, have shown that the interior does matter and contains useful information about the state. So I view this as a challenge to ideas that say that the right generic picture for a black hole consists of a Fuzzball with no interior. However, I think that it is important to understand what the microstates are from the gravity point of view. And so this is what the Fuzzball idea tries to do. And I think this is certainly an important unsolved problem. But I think that giving up on the interior is losing an important part of the physics, and the interior contains interesting information about the quantum state of the black hole or the radiation. Now, more philosophical comment is the interior is the place where the singularity is, and it might be that the singularity is related to this full information, and the full structure of quantum gravity might appear there. Now, I'll give some personal opinion on Fuzzballs. I think that there might well be a basis of states with no interior, perhaps with VR topology near the horizon that exists at some moment in time or on some Cauchy slice. But I suspect that this is likely to collapse into a more standard black hole with a horizon at later times. And this would also, so for extremal black holes, this collapse would be infinitely delayed, and it is likely, there's actually some evidence that there could be a basis of completely horizon-less solutions. But it's quite likely that they have some structure at scales close to the Planck scale. Now, I wanted to make some comments about this point of whether we expect a smooth horizon or not a smooth horizon. But I think, well, this point was made by Shenbin, also similar point. So when we couple the two sides, we get very nice picture that involves quantum teleportation, and it's valid in SYK, and it connects very nicely to the behavior of shock waves in this geometry. While here we wouldn't know what to say. I mean, naively here, the person who gets teleported would die here and get resurrected. And just as a matter of simplicity, it sounds like this picture is giving us the right answer. So I view this as evidence that this is the right way to think about disentangled states. More evidence than the original one. Now, I think there is an important question, which is if a black hole is a fastball and we fall into the black hole, do we die at the horizon or at the singularity? So I interpreted the original proposal as saying that we would die at the singularity and not at the horizon. At the horizon, and there would be no interior. Now then there was this idea of fastball complementarity, where that would say that we still have an interior. And then I feel that the description is a little bit more abstract. I mean, I could replace the word fastball by some representation of the black hole microstate, but we would still need interesting ideas to describe the interior, such as these ideas of entanglement wedge and all the ideas that we've been discussing. So in the recent ideas, we talked about black hole microstates, but we didn't say exactly what they were. And you would need the similar relationships. There was also a question about what ADS-CFT says about this. So, we could imagine a black hole in ADS that in the interior has a huge bag of gold with lots of entropy. And the question is, what does ADS-CFT say about this? Well, ADS-CFT is supposed to describe everything outside the minimal extremal surface, but not the bag of gold. So somehow the bag of gold is described with by something else. The fact that it has entropy means it has entanglement with some other quantum system, and the bag of gold is described by this quantum system. So I think we are learning how to partition spacetimes and assign various portions of the spacetime to underlying quantum systems. Okay, yeah, I think I'll finish here.
Sure, you don't want to make any other comments? Or I saw you had something on JT gravity. Did you want to add to that?
No, well, I think it was not a very good point. So.
Okay. So let's spend a couple of minutes or 2 or 3 minutes on any quick questions to Juan or comments, and then I'll let Samir respond, and then we'll. Any questions? Oh, Stan, go ahead.
Can you hear me?
Yeah, you've got.
I'd like to elaborate on the kind of question on the question that I wrote down in the chat regarding the statement that it's a simple operation to reverse time and recover the moment that is following behind the horizon. I was just wondering if this is happening in a black hole space-time that is radiating fucking quanta, so it is evolving in time. In what sense can reversing time be considered a simple operation?
Yeah, perhaps I didn't express this clearly enough. So in practice for us, reversing time is not easy, okay? But in terms of operations on quantum systems that we can do, it is what's ordinarily viewed as a simple operation, in the sense that it involves a relatively small number of quantum gates. So you have a quantum computer and you're simulating a quantum system. Evolving it backwards in time would be a relatively easy, in terms of complexity theory, operation that you can do.
And the number of fucking quanta is small in some sense.
Yeah, it's an operation which would scale like the number of Hawking quanta and the time you want to evolve backwards. But it scales sort of polynomial in those numbers, but not exponential in the numbers. So in that sense, it is simple.
For young black holes, it would be simple, but for old black holes, it would be harder, I would guess. Would that be true?
You were breaking off, so I didn't understand, but I think that in practice, for an actual black hole we make in nature, it would be extremely difficult for us to reverse time. So in an actual universe, if we make a toy model black hole,
Sorry, go ahead, Ben.
If we made the toy model black hole in a quantum computer, maybe we could reverse time. Okay, but I make this comment just to emphasize that getting the information from inside islands to the outside is supposed to be much more difficult than this. So it's supposed to be exponentially difficult.
Okay. Monica has the last question, and then we'll take a break. So Monica, go for it.
Yeah, so I was just wondering if you could comment on this negative energy mode that Samir talked about behind the horizon. What's your opinion?
Well, I think there are such modes behind the horizon. And they form this bag of gold. Oh, let's see. Well, I wanted to share again, but they form this. Yeah. So we have the evaporating black hole, perhaps, and the radiation that went out of the ADS region. And we have lots of entropy inside the black hole, right? These are typically carried by these negative energy modes or partners of Hawking radiation. And what we learned from the recent discussions is that this region is not described by the CFT, by the Hilbert space or the degrees of freedom in the CFT. I think this has been the main lesson.
Let's say if they're partners of the Hawking radiation, then they should be entangled with the stuff outside, right?
Yeah, they're entangled with the Hawking radiation, and so they're entangled with something outside. Let's say you collected the Hawking radiation in a quantum computer. So this region of the geometry is supposed to be holographic dual, let's say, to the state in this quantum computer. And by doing operations in this quantum computer, we would extract any information we might have put in here.
Okay, thanks.
The statements about reconstruction are always some kind of in the probe limit. So you put in some little qubit that whose state you don't know, and then you are able to reconstruct it from the quantum system.
Okay, I think we should let Samir make 10 minutes or so of remarks, and then we'll have 5 minutes of questions. Then we will break before the panel, give ourselves and the participant, Juan and Samir, particularly time to catch their breath. So Samir, would you share and go for about 10 minutes and make remarks, and then we'll have 5 minutes of questions or so. I don't think we can hear you, Samir, if you're speaking.
Yeah, I'm just trying to get oriented. Can you hear me and see me now?
Yes, can now. Go ahead.
And the screen is being shared?
Yes, all visible.
Okay, so I had a few things on my slides that I still wanted to share. In particular, there was some kind of question I wanted to pose to Juan and others who do this. But first, let me just make a couple of brief remarks on what Juan was just saying. So about this issue of whether two entangled but disconnected CFTs should have this eternal black hole as the dual. What I was talking about in my 2014 paper, which is called What's the Dual of Two Entangled CFTs? It was just the question that if you actually throw a quantum of energy into the right CFT, if the two CFTs are entangled but not interacting, you don't expect to extract the information of that from the left CFT. But if you have this connected diagram, it actually turns out that it seems you can. And why is that? Of course, if you throw something from the right, you might say it just goes into a geodesic and hits the singularity, so it never comes out. But if you look at Hawking evaporation and assume it is unitary, then the information does come out. And if you look at the picture of the eternal black hole, if you throw something from the right, you actually find the information of that in Hawking radiation actually comes out on both sides. And so that was my puzzle with that kind of picture, that if you have two non-interacting but entangled CFTs, in the CFT picture, I throw some information on the right side, like a spin up or a spin down. I should not be able to get that from the left CFT. But in the gravity, if I wait for the Hawking radiation to tell me something, it seemed that I can. Now, you can bypass this by having interactions between the two CFTs. And I think that's what Juan was mentioning. But indeed, if you go to that point, I actually had nothing to say. I mentioned a few of those possibilities in the paper, but I don't have any sharp comments on that. The other comment I had was on this, the Fuzzball complementarity. So there, again, I don't have any slides on it right here, but they might be in my other talks on the web. If you throw some energy, which is E much bigger than T, then what happens is the Fuzzball complementarity is not giving an effective semi-classical description of the black hole that you had to start with. Suppose the black hole had a mass m. It's not like you can average those degrees of freedom to get a effective smooth interior. What is happening when something of E, let's say, equal to 10T falls in, the total number of degrees of freedom you now have accessible in a black hole of mass m plus 10T are much more than the degrees of freedom you had in the original black hole. Okay, so if you just look at the entropies, you will see that. And it's the new degrees of freedom, which are not actually entangled with anything, even if you are past the halfway point or anything. The evolution of those guys is supposed to give you this complementary description. Okay? So the idea that you could even have that is basically the idea of like ADS-CFT duality, right? Something is very simple in one language, but complicated in a different language. But it really is the new degrees of freedom that you come in when you throw something of E much bigger than T. If that could approximately behave like infall, we made a toy model which shows that you can get it. It doesn't mean that you have to get it because the model is a toy model. We don't know if that is true. But it's very important, doesn't work for E of the order of T quanta. So it doesn't actually have anything to do with the information patterns. But let me come to what I have on these slides. And I just have two things. One is I want to say something about something philosophical about ADS-CFT duality. And in the second, I want to pose a maybe reasonably sharp question to the people who are doing JT gravity and wormholes and so on. So I don't know actually any evidence from string theory that we actually have these non-local interactions. And I know in Juan's picture talking about how we can use them to extract something from a black hole. But I would very much like to think about that when we think about small black holes, like something 100 Planck mass is like a small black hole, but should still have black hole physics because 100 is much bigger than 1. So anyway, I'll come to that in a minute. But why are we even thinking of these non-local effects by which out of a bunch of 100 strings here, we don't just have local string dynamics, but we can extract data from somewhere very far away. And why are we thinking about that? And I think the reason might be that one wishes to extend an analogy from ADS-CFT duality, but I will also argue such an extension should not be made, okay? And that the Fuzzball paradigm is already complete. So what did we learn from ADS-CFT duality? It's really beautiful. You take a stack of D3 branes and you throw a graviton onto it. In the open string language, it creates a large number of open strings that make some kind of complicated interacting blob. And then the blob keeps spreading like this. But in some other change of variables, based on open string, you use closed strings. This graviton just smoothly floats down deeper and deeper into ADS space. So what looks very messy in one language looks very simple in the other. And so then you get tempted to say, could there be two descriptions of the black hole? Maybe this very complicated exact description, and then there are these semi-classical guys. You can see I've made these blobs slightly overlap, right? Because when you make approximations, here there are orthogonal degrees of freedom, here there may not be, but the overlap has to be small. And then that's all the small correction theorem story. It's certainly tempting to say that, okay, there must be some approximate thing where this complicated degree of freedom is there with all fuzzballs, but these approximate things are also true. This would be like the open string blob, and this would be like the gravity description. So this suggests that you should be able to do this. It would have been really beautiful if you could, but in fact, it's not possible. So the small correction theorem tells you if you do this, then this theory would need non-local effects. And so I think the reason that we jump from the ADS-CFT idea to applying the same idea to the black hole horizon, it wasn't justified. And the reason it's not justified is that the D3 branes were in a unique ground state. I mean, the boundary of D3 branes is just a single multiple of 256 dimension. It doesn't grow with the number of n. So this dual could just be just one spacetime, ADS spacetime. Entropy was 0 on both cases, so we could represent it by one ADS spacetime. But a black hole is different. The size of a black hole, the surface is determined by the total amount of entropy it contains. And if you have many different states in here, you cannot actually replace them by one state, which is like going to be like a smooth horizon. If you go back like to what's really happening in the small correction theorem, that's really what is getting you. If there are many different states here, you can't approximate them in any way by one state. And so this difference can already be seen when you look at this borderline black hole, the two-charge extremal system where we presumably know everything. So the naive geometry of that, of course, the D1, D5 just goes to a point, but if you and so it looks like one geometry, but this state has entropy, root n1, n5 entropy. If you actually make the microstates, when you come to this horizon surface where the boundary has A over G of the order of the entropy, the microstates start to differ. You cannot actually replace them by one guy. So I think this is what is telling us that when you have surfaces whose size is defined by the amount of entropy they contain, which is different from the ADS-CFT, which is being applied here. Okay, so if you have a D3 branes, the unique bound state, you have using ADS in empty space, everything is no entropy anywhere, you can use ADS-CFT. But if you try to apply that idea to surfaces like the black hole horizon, whose size is determined by the amount of entropy you contain, it doesn't work. And if you still force it to work, I think you get into the non-locality. So even though I love ADS-CFT, I think ADS-CFT just tells us this for black holes, that this is the CFT, and if you put enough energy in the CFT to get to the black hole threshold, you just have this fuzzball inside, and you don't have any of these interesting things like wormholes that we are thinking about. But then for that to agree to this picture and say we don't want this, we have to go back to what I was saying just now. We have to give up the idea of a semi-classical approximation here. It's very ironical. The whole idea of holography came from the black hole, And you can still maybe do things like Fuzzball complementarity for E much bigger than T, but for the actual Hawking radiation quanta, you can't get the simple description because a small correction theorem will force you to non-locality, which I think is not there. So anyway, the whole battle seems to come down to of different perspectives. Fuzzballs are the complete story and nothing more can be done, or no, you want this semi-classical thing and non-locality is part of the real physics of the exact theory. I think these two divergent things are really coming from the desire to impose some idiosyncratic kind of effective physics at the horizon. But I think when a surface is defined by the amount of entropy it contains, at those surfaces, this kind of detailed holography, which looks at Hawking quanta, is not possible. That was just my view on that, and people can take different views on that. But let me just use my remaining like 3 or 4 minutes to talk about a Gedanken experiment that really pinpoint for me the information puzzle and the differences between what the JT gravity people might be saying and what I think happens from fuzzballs. So what I wanted to write down here was the fact, people have talked about all the different words, fine grained versus coarse grained entropy, exact quantum gravity versus semi-classical, black hole seen from outside or inside, local quantum theories, ensemble average theories, and all this obviously is very confusing to the people who don't actively do this. So we're going to cut through across all this and just make a simple concrete Gedanken experiment which illustrates the difference between the fuzzball and the wormhole paradigms to me. Okay. So before that, let's first recall how to check if a state at infinity is pure or entangled, and that's very simple. Suppose you're given an electron and you're asked to find if its spin is in some pure state like this, or an entangled state where here I've entangled it with a muon. Okay. So how would you do that? You just pass it through a Stern-Gerlach apparatus, which is, let's say, is oriented in the z direction. And for this state, you will find half up and half down. And for this state, you'll also find half up and half down. So you haven't been able to tell the difference. But now you try the Stern-Gerlach apparatus oriented in the x direction. And now you find, because this was an eigenstate of sigma x with +1, you'll find they all are in the plus branch. But in this case, you'll find they're still half and half. Okay, so that's how you tell, right? You take some particular electron, you don't have access to the other half, the muon. You want to know if you're entangled, but if you pass it through all different orientations of Stern-Gerlach, you have many, many copies of it, many identically prepared copies. So you can keep doing this. If it is entangled, doesn't matter which way you orient the Stern-Gerlach, you'll always get 50-50. If it is pure, with the appropriate orientation of Stern-Gerlach, you can get 100-0. Okay, so we can definitely do this and do it in the lab. And so this is the experiment. This slide holds everything I was wanted to say about the experiment. Let's start with a PP bar collider, like something at CERN, and make a black hole of 100 Planck masses. It will radiate with 10⁴ quanta. It's all like something small and real there, but 100 is much bigger than 1. So all black hole physics should really be here up to a 99% accuracy, I would think. And then far away from the hole, could be a meter away, the whole black hole evaporates like in this time, some microseconds. Some meter from the hole, you put Stern-Gerlachs, catch all the guys, and just check if it is pure or mixed. Okay, and now the small correction theorem left us with only 2 alternatives. With fuzzballs, you'll find a pure state for the radiation. There was just like a piece of coal. There are no non-local effects in the exact theory, and no effective semi-classical dynamics is allowed for the Hawking quanta. You can't make a semi-classical approximation. And from what I understand in the wormhole picture, you do want a semi-classical approximation, and now you only have 2 choices. This is what I really wanted to focus on. This is my endpoint here. Either the radiation will be measured by in an entangled state by those Stern-Gerlach apparatuses, or the quanta at infinity will behave differently from quanta inside, in the sense that they can be flipped from the quanta at infinity are connected by wormholes to quanta inside. You do something complicated from this, you can influence this. While if you read for the piece of coal, you can't actually influence anybody else. As Juan said, the experiments you need to do to actually use this to influence the interior or other way around might be very complicated. Fine, but in principle, you can. So these quanta are not like these quanta, because whatever you're planning to do with these 100 quanta, you can't do with these quanta. And so let me be even more precise about this. This is my last slide here. We have bypassed many red herrings that are there in this game. We have an arbitrary amount of time to measure these things by the Stern-Gerlach. Sometimes people say it takes too long to measure them, then you can't jump into the hole, but that's irrelevant. If you want to check if the state that came out is pure or entangled, you don't need to jump back into the black hole. The paradox is already there. And you don't have to worry about different kinds of entanglement entropy. One taking into account quantum and gravity effects, one is semi-classical, one is approximate. The Stern-Gerlach apparatus, it really works with the full Hamilton of the real world, right? So all quantum gravity is there. A quantum computer also has everything there. The quantum gravity is there. I'm not switching anything off. I'm just saying, what will you see at CERN when you do this? With a quantum computer, it has 10⁴ bits. Okay, a computer you sell will have that many bits, and it has quantum gravity acting on it. but all the calculations being done when they're designing this doesn't use quantum gravity, and we expect it to work. So one shouldn't think that there are some very hidden, delicate effects of quantum gravity which give you a new kind of entanglement, and there's one kind of entanglement using quantum gravity, one without. There is nothing like that, because the lab only gives you one entanglement in the Stern-Gerlach, and that's the one that we are talking about, right? So here's the entire experiment. You collide the PP bar, make the black hole of 100 Planck, masses, they'll evaporate in a microsecond, collect them a meter away, far away, and let the Stern-Gerlach tell you, is it entangled or not? And I think that the answer I'm finding in the Fuzzball and wormhole cases now are different. I think the Fuzzball people are saying, just like a piece of coal, so nothing else happens. And the wormhole people are saying, we also want this to be a pure state. But this is where I get confused. If they want this to be a pure state, they can't have the semi-classical approximation. If they want this to be an entangled state, that's what I thought I understood from what Juan was saying. This is all, I don't have to distribute an exact semi-classical anything. This is what the lab sees, just that one guy. If the lab is actually going to see an entangled state, then I understand what Juan is saying. It's different from what Fuzzball is saying. There's a baby universe and you entangle the baby universe. But then you shouldn't say the true page curve also
wrap up.
We should just stop here. Go ahead.
Well, take a minute, half a minute, 30 seconds, whatever, to say any final comment. But
okay, I was just about to end anyway. So I was just saying this is the crucial difference that I'd like to ask Juan about. What will the Stern-Gerlach apparatus actually see? Does it see a page curve which has come down, or does it see a page curve which has not come down? And so I think here I will see a difference which is concrete between the Fuzzball and the wormhole paradigms. I will either see a mixed state or I will see something different at infinity. And I think this is the experiment I wanted to postulate here.
So we have a few minutes of questions. So the plan will be that we'll go to about 6 and then break for 20 minutes just to get our breath, and then we'll start the panel. But 2 questions. Edgar's had his hand up, and I put Andrea off to ask her question for Samir after Samir. So Edgar first, then Andrea, and then we'll move on. So
Samir, I don't think we're going to win you over if we don't agree on the thermal field double case. So just at the beginning, you made a comment about why you view the thermal field double as not being dual to the eternal black hole, and you made a statement that if you throw something in from the right CFT, you can access it in either the left or the right. So I think that's not right. I mean, if you could do that, first of all, that would be, just from the bulk point of view, it would be like cloning. And in what you call the wormhole paradigm, the computations actually support this. To access the thing you threw in the interior, you need both the left and right CFTs. So I don't think there's any contradiction there with it being an entangled but uncoupled set of CFTs.
Okay, so let me see if I understand what you just said. My problem was that if you take 2 different CFTs which are entangled, you throw something from the right, you don't want to be able to extract information from the left. I think you're agreeing with that.
Yeah, and in the wormhole picture, that's true.
Yeah, and my problem was that if I go to the dual gravity picture, the thing which I threw in is a particle coming into the interior from the right, and then it can easily cross the horizon, of course, and it goes to, in the horizon, it can break into, let's say, 4 particles. And when you look at what happens to the Hawking radiation, which takes out this information, there is no way to actually prevent some part of the information leaking out from the right horizon and some part leaking out from the left horizon. So we can talk about it more maybe in the discussion session, but this was what I had done in the paper, and I could not see how you would get around that.
Yeah, I mean, you just need the joint state on both sides to access the initial thing. Okay, as you said, some will be out in the left, some in the right. I mean, the words are a little complicated, but you need the joint state to be able to fully access the original thing. But yeah, we can keep talking.
I also want to invite Juan to make a remark about Samir's presentation if he wants to. Just go ahead, Juan.
Well, I think there is no evidence. So in this setup that we were just discussing, there is no evidence that the Hawking radiation will carry the information about the qubit in the wrong side, the side that you don't want it to come. So if you send it from the right, if you send the excitation from the right, there is no evidence that the Hawking radiation will take that information out on the left.
Right. So there's no evidence. My confusion was this. Let's do the following. Let's send 1 particle from the right, 1 from the left. Okay. So in the CFTs, they have to come out right on the respective sides. Now these guys go into the forward wedge inside the horizon. They collide and they break into 3 particles. Okay. Now this information is going to come out, but the information has gotten so badly mixed up, like milk and water. How will you separate what was on the right and what was on the left? That's what I was confused about. 1 part from the right, 1 from the left, they collide inside and they break into 3. Okay. Now each one is mixed with the other, right? Now, how will the theory be clever enough to filter some part which part which came from the right and send it out to the right CFT, right to the right boundary and from the left to the left boundary?
I think that's a good question, but there isn't enough evidence. I mean, there is no evidence to the contrary. So I
can't prove that. It was just like I couldn't see. It looked like a mess. But we can talk about absolutely. I would love to know any ideas that could get me around that.
So I want to know if Andrea wanted to follow up with her question.
Yes.
And also Raphael, I think I also asked to wait. So I don't know whether Raphael wants to jump in with a comment too, but let's just keep it to that. Andrea first.
So I have a two-part question because there's a new one that came in, and that is that, so for extremal black holes, I think there may be agreement that fuzzballs may capture the entropy, like in the D1, D5 or LLM, and correct me if you're not agreeing. And from what you said, it sounded like when you go to the non-extremal case, something new happens. And I wonder if one day one is able to get E to the S microstates from some construction in string theory that one would call fuzzballs, what that new stuff would be, or are you saying that we cannot get that from string theory? Or it has to be, has to have some non-local effects. And the second part of my question is, if we have non-local effects, is there a computation that we can do in order to show that these non-local effects don't mess up any other physics that we know, like any other low energy physics? Like, why is it constrained only to the situation of black holes?
So you're asking me? Okay, so let me comment on the extremal, non-extremal part. I don't have that much to say on the non-local thing. Maybe one should say what the limitations there would be. I think the fuzzballs will have to work equally well for the non-extremal, right? Because some non-extremal fuzzballs have been made, but really for me, the problem is that once you have a horizon, even for one situation, could be non-extremal, you can then use that to run the information puzzle in the small correction. You have to get the non-locality.
So I know your take. That's why I wanted to ask Juan, because he mentioned that for the extremal case, there might be the structure and so on, or it's indefinitely delayed. So I was wondering about the new aspect when we have non-extremality.
Right. Well, this was just my opinion. That's based on the intuition that you could. Well, it's based on the tensor network discussions, where you can take a tensor network and you can cut it, and there is a basis where the tensor network is not very deep, but as you time evolve it, it would get deeper because the complexity of the state increases. And if you make this connection between the length of tensor network being similar to the growth of the interior, and that is, and if you assume that that's related to complexity, then you would expect that generically that complexity should be rising for those states. And so that made me, that makes you think that the interior should grow. If you had the fastballs at some instant in time where no interior, then the interior should start growing as time evolves. So it's based on these observations. But well, I don't know, given that we haven't found the fastballs for the non-extremal black hole, it's just my bet on what will happen.
And what about the question of non-locality? Like, is there a computation that
non-locality? Well, I think that the non-locality for me doesn't have to be more serious than the one we have when we do teleportation, right? So in this example of the two entangled black holes, we send something to the black hole interior, right? And by doing some measurements on the radiation and some measurements on the other stuff that is entangled with the black hole, we can extract it. And I think philosophically, what is happening in all these other, what we need in all these other cases is similar, though the details are different because we cannot extract it as simply. But that's the type of non-locality that I think we need.
Raphael, did you want to make
that particular?
Yeah. Okay.
Yeah, in that particular case, in the bulk, we had a completely local description of what's going on. But it was important that there is an EPR non-locality, so that there is a geometric connection that translates into a geometric connection between the two sides.
Raphael, over to you for the last word for this part.
Yeah, that's too much pressure. It just seems to me that on both sides of this debate, what I'm hearing is sort of one set of really solid results and an overreach that obscures them and gives the other side, something to sort of focus and attack on while overlooking the real benefit of the results the other side has achieved. So in the case of the, what Samir calls the wormhole picture, it's clear, right, that we don't expect the gravitational path integral to be an exact theory. It's not UV complete. It's probably not even well defined. So what we're doing when we play this game is at best a calculational scheme. But it's amazing that that calculational scheme can give you the answer to the entropy of a black hole, as Hawking and Gibbons showed, and even more precisely, the Page curve for a black hole formed from collapse. It had no right to do that, and so we should be happy that it does this, even if it doesn't do many other things like allow us to compute the outstate. And at the same time, on the other side, I think the arguments that Samir pioneered and that were made very precise by AMPS, that there's a conflict between unitarity and a smooth horizon, I think are extremely powerful and solid arguments, and they don't go away because of this new argument that we now found for unitarity. That just means that we still have the problem for the infalling observer, and we need to find a solution for it. And I think that if we don't do this, if we don't try to sort of compare apples and oranges, match an incomplete calculational scheme against an attempt at some UV complete theory like string theory, then we have a lot to learn from each other. So I'm sorry for this kumbaya stuff, but I feel like we're a little bit talking past each other in this conversation.
Okay, good comment, and I think a good one to finish the session on for the moment. I propose that we start again at 18:30 in 25 minutes, because everybody needs, I think, a little bit more space. So we'll just move everything 15 minutes later, if it's okay with everybody. And I'd very much like to thank Samir and Juan for this amazing effort on their behalf. That was fantastic. So thank you very, very much. I'm afraid your work is not quite over, but thank you. I'm most grateful for making a really interesting afternoon, and we will resume